In the beginning, when human beings first looked up at the night sky, what they saw was both wondrous and terrifying. A canvas of twinkling lights suspended in a sea of darkness. Between those stars, they imagined an abyss, a vast nothingness that stretched without end. To them, emptiness was not just absence, it was a haunting presence in itself. For early thinkers, the concept of nothing was as troubling as it was irresistible. Could space itself be truly empty, a void with no substance at all? Or was that emptiness only an illusion born of our limited senses? The Greek philosopher Aristotle refused to accept the idea of a void. To him, nature abhorred empty space. He believed that matter and the medium that carried it were inseparable. In his vision of the cosmos, the heavens were filled with crystalline spheres carrying planets in eternal circular motion, and every place was occupied by something. In such a universe, nothingness could not exist because reality itself would collapse without a medium to hold it together. For nearly 2,000 years, his authority shaped how the Western world thought about the fabric of existence. To Aristotle, the void was not just an impossibility, it was an absurdity. Later, as the centuries unfolded, other thinkers began to push against this view. During the Renaissance, as telescopes revealed new worlds and mathematics offered new tools, the old Aristotelian certainty began to crack. Galileo looked at the heavens and saw not perfect crystalline spheres, but mountains on the moon, blemishes on the sun, and planets wandering in ways that defied neat harmony. Yet even he could not fully escape the belief that some invisible ether or medium pervaded the cosmos. The thought that space itself might be utterly empty still seemed unacceptable. Emptiness was too strange, too frightening, like an abyss with no bottom. Then came Isaac Newton, whose laws reshaped science. Newton proposed that the universe existed within what he called absolute space, an infinite stage that was immovable, eternal, and perfectly still. Objects moved within it, forces acted across it, but the stage itself did not change. Newton treated this absolute space as real, a framework as unshakable as time itself. Yet in doing so, he also gave emptiness a new role. For the first time, space was conceived as something that could exist independently of matter. It was not filled with invisible substances or crystalline shells, but it was still not truly nothing. Newton's space was like a container, vast and silent, into which the cosmos had been poured. The void had been given a name, but it remained an illusion, for Newtonian space was as absolute as the hand of God holding creation in place. For many philosophers, Newton's absolute space was deeply unsettling. Some argued it was metaphysical excess, something beyond what could be observed or measured. How could one prove the existence of space if space itself contained nothing? Others saw it as essential, the hidden scaffolding of the universe. In either case, the notion that the void might truly exist, that between the stars there might be only nothing, still remained impossible to accept. Human intuition revolted at the thought of absence. It was like trying to imagine silence so profound it could not even be heard. This struggle with nothingness was not just philosophical, but psychological. Human beings live in a world saturated with things, with matter, with sensation. Even the air, though invisible, can be felt on the skin, tasted with breath, heard in the whisper of the wind. To imagine space without air, without atoms, without substance, was to imagine a negation so profound that the mind could barely hold it. Every culture, every era, filled the void with something. For the ancients it was ether, a mystical medium that carried light and allowed the heavens to move. For later scientists, it was ether, an invisible sea through which waves of light were thought to ripple. Always there was something, because the alternative, pure nothingness, seemed impossible. Yet history shows that science has always walked a fine line between what feels intuitively right and what evidence demands. Time after time, humanity has had to abandon comforting illusions for stranger truths. The Earth was not the unmoving center of creation, though it felt that way beneath our feet. The sun was not eternal, but a star burning through its finite fuel. Disease was not caused by curses or bad air, but by invisible organisms that thrived in places no eye could see. Again and again, reality proved stranger than belief. And in the case of emptiness, science too would eventually strip away the illusion. The 19th century brought the final test for the ether. Light, as James Clerk Maxwell showed, was an electromagnetic wave, a ripple in electric and magnetic fields. If light was a wave, then surely it needed something to ripple through, just as sound waves needed air and water waves needed the sea. The ether seemed unavoidable, the last refuge of the human need to fill the void. But experiments such as the Michelson-Morley interferometer test in the 1880s revealed nothing. No drift of ether, no hidden medium. Light moved through space as though through nothing at all. This result shocked scientists, but it was undeniable. The ether was gone. The universe appeared emptier than ever. But even then, the idea of true nothingness remained difficult to grasp. Einstein's theory of relativity reimagined space and time as a fabric that could bend and warp under the influence of matter and energy. Space was no longer a container or a background stage, but a participant in the drama of physics. It could curve, stretch, and ripple, but could it be empty? Einstein himself seemed uneasy with that question. He introduced a cosmological constant, a subtle force that held the universe in balance. Though he later called it his greatest mistake, the constant hinted that emptiness might not be so empty after all. The illusion was beginning to crumble. As the 20th century dawned, physics was preparing for an even greater revolution. Quantum mechanics, with its strange rules of uncertainty and probability, would reveal that emptiness is not absence, but presence of a different kind. The so-called void was not silent, but restless, seething with invisible activity. What appeared to be nothing was, in fact, alive with possibility. The human mind, so long afraid of nothingness, would now face the stranger. Truth that nothing is never truly nothing. The failure to detect ether left the scientific community in a strange place. For centuries, it had seemed unavoidable that waves required a medium. Water waves needed the sea, sound waves needed air, and even the idea of light seemed to demand some invisible ocean through which it could ripple. When the experiments of the late 19th century showed no trace of ether, it meant that light traveled without a medium, as if space itself was sufficient. This was a profound break from intuition, and it left many scientists uneasy. The universe was starting to look more empty than ever before, but the meaning of that emptiness was still unclear. To ordinary experience, nothingness hardly exists. When a person shuts their eyes, they do not see pure absence, they see darkness. When sound ceases, silence itself becomes something that can be heard. Even in the stillness of a deep cave, a heartbeat, or the faint echo of breath reminds us that the world is never truly empty. Human beings are surrounded constantly by presence, by sensation, by matter. It is nearly impossible to imagine a condition where nothing at all exists. This is why the idea of emptiness was so troubling. Pure absence has no comparison in the daily world, no example that can be pointed to, and so it resists understanding. Einstein's relativity added an unexpected twist to this puzzle. Space and time were no longer separate backgrounds, but parts of one fabric that could bend and curve in response to mass and energy. This new vision suggested that emptiness was not rigid, not passive, but active and flexible. If a star pressed on it with gravity, space curved, and if a galaxy moved through it, the very fabric shifted. The void was not an absence at all, but a participant in cosmic motion. To say that space was empty seemed less and less accurate, because emptiness was now revealed as a thing that could ripple, bend, and even expand. Yet the deeper question remained unsettled. Could there truly be a region without matter, without fields, without content of any kind? Astronomy offered glimpses of this mystery. Looking into the night sky, telescopes showed that between stars and galaxies were vast stretches of darkness. Measurements revealed that a cubic meter of interstellar space might contain only a handful of hydrogen atoms, so sparse that calling it empty felt almost natural. Yet even here, there was something. Compared to the air we breathe, which contains countless molecules in every breath, the space between stars was unimaginably thin, but never perfectly vacant. A single atom drifting in a cubic meter meant that the void was never fully void. Emptiness was always approximate, never exact. The laboratory confirmed this truth. Scientists created vacuums by pumping chambers until pressure fell to levels undetectable by their instruments. These chambers were called empty, but they were not perfect nothing. Stray molecules always lingered, bouncing invisibly. The ideal of absolute emptiness, like the concept of absolute zero temperature, seemed unreachable. One could approach it, but never achieve it. This gave emptiness the strange quality of being both real and imaginary, a limit that could be defined but not touched. It was there in theory, but not in practice. Philosophers seized on this problem. If emptiness could not exist physically, was it only a mental construct, a product of language rather than nature? Or was it a boundary condition of the universe, something that shaped reality even if it could not be experienced directly? These questions blurred the line between physics and metaphysics, because to understand emptiness was to understand not just matter, but the very stage on which matter appeared. Human beings had long filled that stage with assumptions, imagining ether, or divine frameworks. The collapse of those ideas forced people to stand face to face with the possibility that the universe had no hidden support, no medium, just vast stretches of apparent nothing. Still, even in this apparent absence, science was moving toward an unexpected discovery. At the beginning of the 20th century, new experiments in atomic physics revealed that the universe was stranger than classical theories had imagined. Atoms, once thought to be tiny solid balls, were revealed to be mostly empty space themselves, with nuclei thousands of times smaller than the atom as a whole, and electrons dancing around them like faint whispers. The atom was almost entirely void, yet it held the structure of matter itself. Here again, emptiness was shown to be deceptive. What seemed solid was mostly space, and what seemed absent carried profound effects. This realization prepared the ground for the greatest shift of all. As quantum mechanics began to emerge, it suggested that emptiness was not absence but activity of a hidden kind. The void was not barren but alive, restless, and filled with invisible processes. What centuries of philosophy had feared and what science had resisted would soon become the foundation of modern physics. The illusion of emptiness was breaking down, and the truth that followed would be more extraordinary than anyone had imagined. By the time the 20th century took hold, the illusion of emptiness had been weakened, but not destroyed. The ether was gone. Newton's absolute stage was replaced by the fabric of space-time, and atoms were revealed as mostly void. Yet the human desire to find substance in the emptiness endured. What scientists were beginning to discover was that emptiness itself had secrets. Secrets far stranger than the old philosophical debates about fullness and void. The emptiness of space and the emptiness inside atoms were not silent gaps, but realms of hidden motion. The structure of the atom was one of the great shocks to human understanding. For centuries, atoms had been imagined as indivisible particles, the solid grains of reality from which all matter was built. But the discovery of the nucleus and the electron revealed that the atom was not a solid ball, but a miniature solar system of sorts, with a dense core surrounded by empty space. If the nucleus of an atom were the size of a pea, the electrons would orbit far away at the edges of a cathedral, leaving everything between them empty. Ordinary matter, the wood of a table, the iron in a nail, even the cells of our bodies, were composed almost entirely of emptiness. The solidness we feel when pressing our hand against a wall is not atoms colliding like billiard balls, but electrical forces repelling one another across gaps of empty space. This revelation forced people to reconsider what they meant when they spoke of emptiness. If matter itself was mostly empty, then the void was not just between stars or within evacuated chambers, but inside every atom of existence. The illusion of solidity was as deceptive as the illusion of emptiness. Reality seemed to hover between presence and absence, between something and nothing, in ways that defied intuition. What once had been philosophy was now becoming experimental fact. At the same time, light itself revealed the strange character of emptiness. It behaved as both wave and particle, refusing to fit neatly into classical categories. In the double-slit experiment, single photons passed through two slits and created interference patterns as though they were waves interfering with themselves. Even when fired one at a time, photons accumulated to form patterns that required an explanation beyond simple particles. These behaviors hinted that emptiness was not a simple stage where particles moved, but a domain where probability, uncertainty, and wave-like behavior governed reality. The emptiness of space was active in a way no one had expected. The more scientists probed, the stranger emptiness became. Radioactivity showed that even seemingly stable atoms could erupt with energy from within, as though emptiness itself held potential waiting to be released. Subatomic particles revealed behaviors that defied classical logic, tunneling through barriers, appearing and vanishing in ways that suggested the fabric of reality was less rigid and more fluid than once thought. Emptiness was not the end of matter, but the beginning of a new kind of understanding. For the human imagination, this was disorienting. Nothingness had once been terrifying because it seemed like absence, like the void into which existence might collapse. Now, nothingness was becoming terrifying for a different reason. It was no longer absence, but abundance of an unseen kind. The atom, which should have been a simple building block, was instead a realm of forces and spaces and possibilities, most of it empty and yet rich with hidden dynamics. The void was not dead silence, but a place where the very laws of physics whispered constantly. It was here, on the border between classical physics and quantum mechanics, that the illusion of emptiness would finally shatter. Scientists were preparing to describe reality not in terms of objects moving through empty containers, but in terms of fields that extended everywhere, even into what appeared to be void. The concept of nothing was about to be overturned completely. Space would soon be recognized not as emptiness, but as a sea of energy, invisible yet present everywhere. The illusion of emptiness was ending, and a new vision was rising, one in which the void itself was alive. The deeper scientists peered into reality, the more they realized that emptiness was not something simple. What once had seemed a clear divide between matter and void began to blur. Matter was not solid, but mostly empty space, and space itself, far from being nothing, carried shape and curvature. Even the language of physics began to shift. Emptiness was no longer described as absence, but as structure, something that could be measured and studied, something that could bend under gravity and transmit light. The human story of emptiness had come full circle in a way. In ancient times, philosophers like Aristotle denied the existence of a void because it seemed impossible for nothing to exist. Centuries later, Newton gave emptiness a stage-like quality, treating it as absolute space that could exist even without matter. Then came the failure of ether, which left scientists facing the shocking possibility that emptiness might indeed be real. Finally, relativity revealed space itself as a fabric that could move and curve, while atomic physics showed that matter was mostly empty space. At each step, what was once thought to be nothing turned out to be something, and what was thought to be something was revealed to be mostly nothing. The consequences of this shift were profound. Human beings were forced to see themselves differently, no longer as creatures living in a universe of solid matter moving through empty void, but as part of a cosmos where solidity was an illusion and emptiness was active. Every breath of air, every piece of stone, every living cell carried within it more emptiness than substance. The world was woven from space, not filled with matter. To realize this was to realize that the universe itself was stranger and more fragile than once imagined. This realization carried a philosophical weight as well. If emptiness was not an absence but an active player in the universe, then nothingness was not the opposite of existence but part of it. The boundary between something and nothing had dissolved. Even language seemed inadequate. To say that an atom was empty was true, yet it was also filled with electric fields and quantum probabilities. To say that space was empty was true, yet it was also filled with curvature and light. Words that once carried sharp distinctions now blurred into paradox. Nothingness could no longer be dismissed as void. It was part of the structure of reality. By the early decades of the 20th century, the stage was set for the next revolution. Scientists had revealed the emptiness inside atoms, and experiments were beginning to uncover the strange behaviors of electrons and photons. The old world of certainty was dissolving into one of probability and chance. The concept of the vacuum, once thought to be the absence of everything, was about to be redefined in ways that would challenge both physics and philosophy. The illusion of emptiness was ending, not with the discovery of void, but with the discovery that the void was full. This moment in history was more than a scientific transition. It was an existential one. To the ancient mind, nothing was a fearsome abyss that nature could not tolerate. To the modern mind, nothing was revealed as a profound presence, a sea of hidden order that sustained the cosmos. The journey from Aristotle to Einstein showed that emptiness was not an absence, but a mystery, waiting to be unfolded. And as the 20th century advanced, it would be quantum mechanics that finally pulled back the veil. In the world of the very small, the vacuum would reveal itself as a storm of invisible particles, a place where energy never rested, and where nothing itself became the foundation of everything. And so, the illusion of emptiness dissolved. Space was no longer the silent void it had once appeared to be. The emptiness that haunted the philosophers and challenged the scientists was in truth alive, restless, and essential. The stage was ready for the next chapter, in which the quantum vacuum would emerge, showing beyond doubt that nothingness does not exist. What seems empty is in fact one of the most powerful realities of the universe. By the dawn of the 20th century, science had stripped away the old illusions of emptiness. The ether had been discarded, atoms had been revealed as mostly void, and relativity had shown that space itself was a fabric capable of bending and stretching. Yet the deeper scientists looked, the clearer it became that what they had called emptiness was hiding something extraordinary. The greatest surprise of modern physics was that the vacuum of space is not empty at all. It is alive, restless, and filled with invisible energy. This revelation, born from quantum theory, changed forever the meaning of nothingness. The breakthrough came with the development of quantum mechanics in the 1920s. Classical physics had imagined that if you removed every particle from a region of space, what remained was true emptiness. But quantum physics rejected that idea. Instead, it showed that reality is built not from particles alone, but from underlying fields that fill all of space. Every kind of particle corresponds to a field. Electrons arise from the electron field, photons from the electromagnetic field, quarks from their own fields, and so on for every building block of matter. These fields are not optional. They exist everywhere, even where no particles are present. Space, in this view, is never a blank canvas. It is always threaded with fields that cannot be removed. This understanding transformed the meaning of the word vacuum. In everyday language, a vacuum is simply an absence, a space emptied of air or matter. But in quantum field theory, the vacuum means something very different. It is the lowest possible energy state of all the fields that fill the universe. Even in this lowest state, the fields are still there. They cannot be switched off, and they cannot be erased. Thus, the quantum vacuum is not an absence, but a presence, a foundation that underlies reality. The reason this vacuum is alive lies in one of the most fundamental principles of quantum mechanics, the uncertainty principle. Werner Heisenberg discovered that certain pairs of physical properties cannot both be known with infinite precision. Position and momentum, for example, cannot both be fixed. The same is true of energy and time. This principle means that nature does not allow complete stillness. Even in its lowest energy state, a field cannot be perfectly calm. It must always fluctuate slightly, jittering with unavoidable uncertainty. This restless activity is not noise in the system. It is built into the rules of reality itself. From this unavoidable jitter emerges one of the most striking consequences of the quantum world, the appearance of virtual particles. These are not particles in the sense of stable electrons or protons that persist through time. Instead, they are brief excitations of the underlying fields, flickering into existence for a fraction of a second and then vanishing again. They are born in pairs, a particle and its antiparticle, which annihilate one another almost immediately. According to the uncertainty principle, these momentary appearances are allowed, provided they vanish quickly enough. To human senses, space looks silent. But in truth, it is a storm of virtual particles appearing and disappearing without end. This strange picture might sound like imagination, yet it is grounded in experiments and theory of extraordinary precision. Quantum electrodynamics, the theory that unites light and matter, relies on the existence of vacuum fluctuations. When physicists calculate the magnetic properties of the electron, or the way light shifts the energy levels of atoms, they must include the effects of these fluctuations. Without them, the numbers do not match reality. With them, the agreement between theory and experiment is astonishing, extending to more than 10 decimal places. Such accuracy cannot be coincidence. It is evidence that the vacuum is real, and that its invisible fluctuations shape the universe. The revelation was astonishing because it overturned centuries of thought. For millennia, nothing had been defined as absence. The void was either denied, as Aristotle had done, or treated as an empty container, as Newton had imagined. Now science revealed that the void does not exist at all. Even when matter is gone, fields remain. Even when energy is minimized, fluctuations continue. The vacuum of quantum physics is not nothingness, but a hidden foundation, alive with constant motion. It is one of the most profound discoveries in human history. The discovery that the vacuum is alive with energy is difficult to accept because it runs against everything our senses tell us. When we walk into an empty room, we see space devoid of objects. When a bell stops ringing, we hear silence. In daily life, Emptiness seems simple, a lack of presence. But the quantum vacuum is not absence. It is a restless background that we do not see, a hidden activity beyond ordinary perception. To grasp this, one must accept that reality is layered. The world we touch and hear is built upon another world, one that is invisible but more fundamental. The reality of the quantum vacuum first became undeniable through subtle experimental signatures. One of the earliest examples was the Lamb shift, discovered in 1947 by Willis Lamb and Robert Rutherford. When they studied the hydrogen atom with precise microwave techniques, they found that one of the electron's energy levels was slightly higher than predicted by earlier theory. The difference was small, but it was real and measurable. The explanation came from vacuum fluctuations. The electron was not orbiting in silence, but in a sea of restless fields that nudged it ever so slightly. This invisible influence shifted the energy of the atom. What looked like emptiness was actively changing the rules of matter. This was a turning point. It meant that the vacuum was no longer just an abstract mathematical concept, but a measurable presence in the laboratory. The Lamb shift was not speculation, but proof that the vacuum has consequences. The void was not a ghost, but a partner in the structure of the atom. It was as though empty space had reached out and left its fingerprint on hydrogen itself. The same story unfolded in the study of the electron's magnetic moment. This property describes how the electron behaves when placed in a magnetic field. Quantum electrodynamics, the theory developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, provided a way to calculate it with incredible precision. But the calculation only matched experiments when vacuum fluctuations were included. The restless sea of virtual particles had to be taken into account. The agreement between theory and measurement extended to more than 10 decimal places, making it one of the most accurate predictions in the history of science. Without the vacuum, the numbers failed. With the vacuum, the universe made sense. These results forced physicists to rethink the meaning of emptiness. For centuries, emptiness had been defined as absence, but the quantum vacuum proved that absence itself does not exist. Even when every particle is removed, even when all energy is minimized, fluctuations remain. They are unavoidable, built into the rules of quantum mechanics. The universe has no perfect silence. The vacuum is always humming. The implications are staggering. If the vacuum fills every point of space, then no region of the universe is ever truly empty. Between stars, between galaxies, even in the depths of intergalactic voids where only a few atoms drift across light years of distance, the vacuum is still present. It is not a property of certain places, but of all places. No matter where you go in the cosmos, the vacuum follows. Nothingness is an illusion. Everywhere is filled with energy, even if invisible. This recognition carried philosophical weight as well. For the first time, science had shown that nothing is not the opposite of something but its foundation. The vacuum is not the enemy of matter, but the source from which matter emerges. The silence of space is not empty silence, but a hidden symphony, playing beneath the threshold of human perception. This shifted not only physics, but philosophy. To ask about the nature of emptiness was no longer to ask about absence. It was to ask about the ground of reality itself. The more carefully physicists studied the vacuum, the more they realized it was not a passive background, but an active player in the laws of nature. The forces that hold atoms together, the way light interacts with matter, and the very constants of physics all depend on vacuum fluctuations. Without them, matter would not behave as it does. The vacuum is not just there. It is shaping the universe. By the mid-20th century, the concept of the quantum vacuum had become unavoidable. Experiments had confirmed it. Theory had explained it. and philosophy had begun to reckon with it. What had once been seen as nothing had become one of the most powerful realities of existence. But this raised a new question. If the vacuum is real and active, could its effects be measured directly, not just in subtle atomic shifts, but in visible forces in the laboratory? The stage was set for one of the most remarkable predictions in modern physics, one that would soon reveal the vacuum's power in a way that could no longer be doubted. The realization that the vacuum was filled with restless energy transformed not only physics, but also imagination. For centuries, emptiness had been dismissed as absence, a silent background with no role to play. Now it was revealed as active, shaping atoms, altering forces, and influencing the very laws of nature. This meant that space itself was alive. To scientists of the mid-20th century, this was both unsettling and thrilling. It meant that the foundation of reality was stranger than anything classical physics had ever allowed. One of the most striking aspects of this discovery is the way virtual particles behave. According to the uncertainty principle, pairs of particles and antiparticles can appear briefly, borrow energy from the vacuum, and then annihilate back into nothing. They leave no permanent trace, but during their fleeting existence, they can interact with real particles. An electron moving through space is constantly jostled by these virtual pairs, its behavior altered by encounters with particles that do not officially exist. The fact that something so ghostly could influence real matter showed just how thin the line between presence and absence had become. The scale of these fluctuations is immense. They occur everywhere, at every point in space, and at every moment in time. No region of the cosmos is exempt. Whether inside an atom, in the vacuum between stars, or across intergalactic space, virtual particles are flickering in and out of being. The density of this activity is astonishing. If the energy of the vacuum could somehow be collected, it would vastly exceed the energy contained in all the visible matter of the universe. Of course, the laws of physics prevent such direct extraction, but the very fact that the vacuum contains such enormous energy challenges intuition. The void is richer than the sum of galaxies. These fluctuations do not remain hidden. Their fingerprints appear in measurable phenomena. Quantum tunneling, for example, relies on the uncertainty principle and the restless nature of the vacuum. Particles that should be trapped behind barriers can, through fluctuations, appear on the other side. This process is not only a theoretical curiosity, but essential to the functioning of stars. Nuclear fusion in the core of the Sun depends on tunneling. Without the restless fluctuations of the vacuum, the Sun would not shine, and life on Earth would not exist. In this sense, every breath we take is a gift from the quantum vacuum. Another place where the vacuum reveals itself is in the stability of matter. The forces that hold protons and neutrons together in atomic nuclei are influenced by virtual particles. Gluons, the carriers of the strong nuclear force, are constantly interacting with virtual quark pairs that emerge from the vacuum. These ghostly interactions affect the mass and structure of the nucleus. Without the constant influence of vacuum fluctuations, matter would not exist in its present form. The solidity of the world, the reality of mountains, oceans, and living beings depends on the invisible energy of what was once called nothing. The more scientists uncovered, the more profound the implications became. If the vacuum was so fundamental to the existence of matter, then it was not just a background, but an essential player in the cosmic drama. The vacuum was shaping everything, from the smallest particles to the largest structures in the universe. The recognition of this fact forced a shift in perspective. The void was no longer emptiness. It was the very fabric of reality, the stage not just for matter, but for the laws that governed it. This understanding also raised new questions. If the vacuum was real and active, then perhaps its influence extended beyond atoms and stars to the universe itself. Could the energy of the vacuum determine the fate of the cosmos? Could it drive cosmic expansion or shape the evolution of galaxies? These questions were not answered in the early decades of the 20th century, but the seeds had been planted. The vacuum was no longer a minor curiosity. It was a central problem in physics, one that demanded attention. And yet, for many physicists, the idea of probing the vacuum more directly remained irresistible. Subtle effects like the Lamb shift and the electron's magnetic moment were powerful evidence, but they were indirect. What if the vacuum could be made to reveal itself through forces that could be seen and measured directly in the laboratory? Such a discovery would silence doubt and prove beyond all question that emptiness was alive with energy. It was this search that would soon lead to one of the most remarkable predictions in modern physics, a prediction that would bring the invisible power of the vacuum into measurable form. By the middle of the 20th century, the picture of the vacuum had shifted completely. What had once been dismissed as nothing was now recognized as the most fundamental something of all. But the story was not finished. For all the indirect evidence that vacuum fluctuations existed, physicists still hungered for a way to see their effects more directly. Experiments with atoms and electrons had confirmed the vacuum's presence, but they required precision instruments and careful interpretation. What the scientific community wanted was a test that could show in a clear and undeniable way that empty space could produce measurable forces of its own. It was in this context that the Dutch physicist Hendrik Casimir made a bold prediction in 1948. He suggested that two uncharged metal plates placed extremely close together in a vacuum would experience an attractive force. At first glance, this seemed impossible. If there were no particles between the plates and no electrical charges pulling them together, why would they move at all? Classical physics predicted nothing, but Casimir argued that the restless vacuum itself would create a pressure difference. The plates would suppress some of the virtual particle fluctuations between them, allowing more fluctuations outside than inside. This imbalance would push the plates toward each other. In other words, empty space would create a force where none should exist. This prediction was extraordinary because it suggested that the vacuum was not only real, but capable of producing measurable mechanical effects. It meant that emptiness itself could push on matter. Though the force would be extremely small, detectable only when the plates were separated by microscopic distances, it was a direct consequence of quantum field theory. Casimir's idea gave scientists a way to bring the abstract concept of vacuum energy into the realm of experimental physics. It promised a demonstration that emptiness is never truly empty. At the time, the prediction was greeted with fascination, but also with skepticism. The idea that nothing could exert a force was deeply counterintuitive. Yet the logic was airtight. If the vacuum is filled with fluctuations, then restricting those fluctuations changes the energy of the system. That change in energy must produce a measurable effect. Casimir had turned the philosophical problem of emptiness into a concrete scientific proposal. If confirmed, it would prove beyond doubt that the vacuum is alive. The eventual experimental confirmations of this effect would not come until decades later, with the development of sensitive techniques capable of measuring forces at the microscopic scale. But even before the experiments were carried out, Casimir's prediction captured the imagination of physicists. It showed that the vacuum was not a distant abstraction, but something that could be touched and measured in the laboratory. It made the invisible power of empty space tangible. The Casimir prediction was more than a clever idea. It was a milestone in the story of physics. It demonstrated that the vacuum could no longer be thought of as nothing, nor even as a passive stage for the universe. It was a dynamic field with energy, capable of shaping the behavior of matter on scales large and small. The void was revealed as a participant in the workings of the cosmos. In time, the Casimir effect would become one of the most compelling proofs of the quantum vacuum, but even in theory, it marked a turning point. The journey from Aristotle's denial of the void to Newton's absolute space, from the fall of the ether to the rise of quantum field theory, had reached its climax. The illusion of emptiness was gone. In its place was the recognition of a restless, energetic vacuum that pervades all of reality. The vacuum is not silence, it is a hidden symphony, its fluctuations shaping everything from the structure of atoms to the fate of stars. What had once been dismissed as absence is now seen as the very foundation of existence. As the 20th century advanced, experiments would begin to catch up with Casimir's vision. The attraction of plates in a vacuum would be measured, confirming that space itself produces forces. These demonstrations would pave the way for new explorations of the vacuum, showing that emptiness is not a void to be feared, but a reality to be embraced. The next step in this journey would take place not in theory, but in the laboratory, where the invisible power of empty space would be revealed beyond doubt. By the middle of the 20th century, the concept of the quantum vacuum had grown from a bold idea into a necessity of physics. Subtle shifts in atomic energy levels, the behavior of electrons, and the success of quantum electrodynamics all pointed toward the reality of a restless, energetic vacuum. Yet for all this evidence, many physicists longed for something more direct. The Lamb shift and the magnetic moment of the electron were powerful confirmations, but they were subtle and required careful interpretation. What the scientific community wanted was an experiment that could demonstrate in plain, undeniable terms that the vacuum itself could push and pull on matter. It was in 1948 that Hendrik Casimir, a Dutch physicist working at the Philips Research Laboratories, proposed such a test. He suggested that two parallel metal plates, placed extremely close together in a vacuum, would feel an attractive force drawing them together. At first, the idea seemed outrageous. The plates were uncharged, meaning there was no electric attraction. There were no atoms or molecules between them to exert pressure. Classical physics predicted nothing at all should happen, but Casimir argued that the quantum vacuum would behave differently. The reasoning came directly from the restless nature of vacuum fluctuations. Empty space is filled with virtual particles and fluctuating electromagnetic waves. Normally, these fluctuations occur everywhere, in every wavelength, with no restrictions. But when two plates are placed close together, they impose boundary conditions. Only certain wavelengths of fluctuations can exist in the narrow gap between them, while outside the plates, the full range of fluctuations remains. This imbalance in allowed modes creates a pressure difference. There are more fluctuations outside than inside, and this difference pushes the plates toward each other. Casimir's prediction was extraordinary because it suggested that emptiness itself could generate a measurable force. The plates, in effect, would be squeezed together by nothing. The force was small, far too weak to be detected with the technology of the 1940s. But the principle was clear. If confirmed, it would be one of the most dramatic demonstrations in all of physics. Proof that the vacuum is alive with energy. The Casimir effect, as it came to be known, soon captured the imagination of scientists. It provided a concrete way to test what had previously been abstract. The vacuum would no longer be a theoretical sea of fluctuations inferred only through subtle atomic shifts. It would become something tangible, capable of moving objects in the laboratory. For a field as abstract as quantum mechanics, this was a revelation. It showed that even the strangest predictions could give rise to experiments in the real world. Casimir himself did not live to see the full experimental confirmation of his idea, but his prediction became a milestone in the story of modern physics. It represented a turning point where the vacuum ceased to be a hidden background and became a measurable participant in reality. The quantum vacuum once dismissed as imagination, was now producing a physical force that scientists could in principle measure. The idea that nothing could act like something was no longer philosophy, it was science. The concept also carried philosophical weight. For centuries, the void had been a battleground between presence and absence, between being and nothingness. Casimir's prediction shifted the ground entirely. It showed that what we call nothing is in fact structured. It has properties. It can create forces. The vacuum is not an absence, but a field of energy that shapes matter. The implications stretched far beyond the laboratory. If nothing could act like something, then perhaps emptiness itself played a role in the cosmos at large. This realization set the stage for one of the most fascinating chapters in physics. In time, experiments would confirm Casimir's prediction, demonstrating that the vacuum does not merely influence atoms or electrons, but can exert forces on macroscopic objects. The invisible ocean of quantum fluctuations was no longer hidden. It was real, measurable, and undeniable. The illusion of emptiness had been destroyed once and for all. When Hendrik Casimir first proposed his prediction in 1948, the idea seemed far beyond the reach of experiment. The force between the plates was real in theory, but it was extraordinarily small. To detect it, two metal plates would need to be positioned only a few hundred nanometers apart, thinner than the width of a human hair, and held perfectly parallel. Even a tiny tilt or vibration could overwhelm the signal. In the 1940s, no laboratory possessed instruments capable of controlling such delicate conditions. The Casimir effect was fascinating, but for the time being, it lived only in the realm of theory. Yet the prediction lingered in the minds of physicists. It was too elegant, too simple, and too profound to ignore. The idea that nothing could produce a force was one of the most dramatic challenges to classical intuition ever proposed. Over the next decades, as experimental techniques advanced, scientists began to imagine ways to test it. The development of vacuum technology, sensitive detectors, and precision engineering in the second half of the 20th century made the impossible seem gradually more achievable. One of the earliest attempts came in the 1950s, when Marcus Spanay, a Dutch physicist and colleague of Casimir, tried to measure the effect. Spanay reported results that hinted at the predicted force, but the uncertainties were too large to be conclusive. The technology of the time could not yet provide a clean measurement. The Casimir effect remained unproven, a tantalizing ghost hovering at the edge of physics. For decades, the challenge persisted. To bring two plates close enough without touching, to keep them aligned, and to measure the tiny force pressing them together required extraordinary skill. The force is so small that even the slightest electrostatic charge, thermal vibration, or surface roughness could obscure it. Many physicists wondered whether the effect could ever be detected directly. Still, the prediction stood. The mathematics was sound, and the logic was undeniable. The question was not whether the Casimir effect existed, but whether humanity could build tools delicate enough to see it. By the 1990s, technology had finally caught up. Advances in nanotechnology and precision measurement allowed scientists to probe distances at the scale required. In 1997, Steve Lamoureux at Los Alamos National Laboratory performed one of the first definitive measurements of the Casimir force. Instead of using two perfectly parallel plates, which was nearly impossible to achieve, he measured the force between a flat plate and a spherical surface. This geometry simplified alignment and allowed for more practical testing. The result was clear. The measured force matched Casimir's prediction to within a few percent. Empty space had revealed its hidden strength. The confirmation electrified the physics community. Nearly 50 years after Casimir's proposal, the vacuum had spoken. The experiment showed that two objects, uncharged and isolated in a vacuum, could attract each other because of suppressed quantum fluctuations. Nothing had created a force, and that force could be measured. The Casimir effect was no longer theory, it was fact. Since then, further experiments have refined the measurements. Improved techniques have reduced errors, explored different materials, and confirmed the effect with increasing accuracy. Researchers have even studied how changing the properties of the surfaces, their conductivity, temperature, or shape, alters the Casimir force. These studies have revealed that the vacuum is sensitive to boundaries and conditions, as though emptiness itself adapts to the presence of matter. The vacuum is not passive. It responds, and it acts. The confirmation of the Casimir effect was a milestone because it demonstrated the physical reality of the quantum vacuum in the clearest possible terms. No longer was the vacuum an abstraction hidden in the equations of quantum field theory. It was a measurable presence, capable of exerting forces on macroscopic objects. The illusion of emptiness had not only been broken in theory, but shattered in practice. The laboratory had proven that nothingness is alive. For philosophy as well as science, this was a profound moment. It showed that the old debates about the void, stretching back to Aristotle and Newton, through the fall of ether and the rise of relativity, had been resolved not by argument, but by experiment. The vacuum is not absence. It is a structured reality with measurable consequences. What once seemed impossible to prove had now been demonstrated with instruments built by human hands. The void had become tangible. The Casimir effect also opened new questions. If vacuum fluctuations could produce measurable forces in the laboratory, what might they do on cosmic scales? Could they influence the behavior of the universe itself? Could the energy of empty space be the key to explaining mysteries like dark energy and cosmic acceleration? These questions would push physics into uncharted territory, where the smallest scales of quantum mechanics met the largest scales of cosmology. The experimental confirmation of the Casimir effect was not the end of the story. It was only the beginning. Once the force predicted by Hendrik Casimir was proven to exist, scientists began to explore it in greater detail. The vacuum was no longer a silent backdrop. It was an actor with measurable influence, and now the task was to understand the extent of its role. One of the first questions researchers asked was how the Casimir force depended on distance. Casimir's original calculation predicted that the force would grow stronger as the plates came closer together, increasing dramatically at nanometer scales. Experiments confirmed this. The closer the surfaces, the greater the force pressing them together. This meant that in the microscopic world, the Casimir effect is not a curiosity but a dominant force. At separations of only a few nanometers, the Casimir attraction can rival or even exceed the electrical forces that bind molecules. The vacuum, invisible to the eye, becomes a powerful presence at the smaller scales. The geometry of the objects also turned out to be important. Casimir had considered two flat plates, but in practice, experiments used spheres, cylinders, and irregular shapes to make alignment easier. Each geometry altered the distribution of allowed fluctuations in the vacuum, changing the strength of the force. Physicists developed sophisticated techniques to calculate these effects, and experiments confirmed them. The vacuum was revealed to be highly sensitive, responding differently depending on how matter shaped the space around it. Emptiness, it seemed, had a geometry of its own. Another question was whether the Casimir force could be repulsive, as well as attractive. For decades, it was assumed to be only attractive, pulling objects together. But theoretical work showed that under certain conditions, such as with materials of particular electromagnetic properties, or in the presence of fluids, the force could become repulsive. Experiments in the early 21st century confirmed that Casimir forces could indeed push as well as pull. This discovery opened a new avenue of research, showing that the vacuum is even more versatile than first imagined. These insights quickly attracted the attention of engineers working at the frontier of nanotechnology. At the scale of microchips and nanoscale devices, the Casimir force is not negligible. It can cause tiny moving parts to stick together or resist motion, creating challenges for the design of microelectromechanical systems. At the same time, researchers began to explore whether Casimir forces could be harnessed rather than avoided. By carefully choosing materials and geometries, it might be possible to design devices that use the vacuum's invisible push and pull for practical applications. What was once a philosophical puzzle had become an engineering reality. The Casimir effect also provided a unique testing ground for fundamental physics. Because the force depends on vacuum fluctuations, measuring it with increasing precision allows physicists to test the limits of quantum field theory. Some experiments have looked for tiny deviations from the predicted force, which could hint at new physics beyond the standard model or even extra dimensions of space. While no such deviations have yet been found, the Casimir effect remains one of the few ways to probe the vacuum directly, making it a powerful tool for exploring the boundaries of knowledge. In the last few decades, experiments have pushed the accuracy of Casimir measurements to remarkable levels. Using sensitive torsion balances, atomic force microscopes, and microfabricated devices, researchers have confirmed the theory with ever greater precision. These experiments have not only verified Casimir's prediction, but also mapped out the ways the force changes with geometry, temperature, and materials. The vacuum has revealed itself to be responsive, almost like a medium that can be tuned and shaped. The philosophical implications remain profound. The Casimir effect is not a force arising from particles or fields we can see, but from the absence of them. It is born from the suppression of possibilities, from the modes of fluctuation that cannot exist between the plates. Nothingness itself creates the force. This challenges not only physics, but human intuition. It shows that absence is never truly absence, and that the universe does not allow emptiness to exist without consequence. The experiments of the late 20th and early 21st century transformed the Casimir effect from a bold prediction into a well-established fact. What began as a thought experiment in 1948 became a cornerstone of modern physics. The vacuum, once dismissed as nothing, was now known to be a sea of energy capable of producing real forces. Every confirmation of the Casimir effect drove home the same lesson. Emptiness is not empty. It is alive, structured, and powerful. As research advanced, scientists began to connect the Casimir effect to broader questions about the universe. If vacuum fluctuations can produce forces in the laboratory, might they also play a role in cosmic phenomena? Could the energy of the vacuum help explain mysteries such as dark energy or the expansion of the universe? The laboratory had shown that the vacuum has power. The cosmos itself would soon reveal just how much. The Casimir effect had begun as a daring idea, a mathematical prediction about the hidden activity of the vacuum. By the time it was confirmed in experiments in the late 20th century, it had become one of the most striking demonstrations of quantum reality. Nothingness, once thought to be the simplest of concepts, had revealed itself to be one of the most complex. Two metal plates, uncharged and isolated in a vacuum, moved toward each other not because of forces we could see, but because of the restless fluctuations of empty space itself. This result marked a turning point in the human understanding of nature. For centuries, philosophers had argued about the existence of the void. Aristotle had denied it, Newton had described it as absolute space, and 19th century physicists had filled it with ether. The Casimir effect settled the debate in the most concrete way possible. Emptiness is not nothing. It has measurable consequences. The void has structure, it has energy, and it can reach out and move matter. The philosophical debates about nothingness were resolved not by argument but by experiment. The laboratory proof of the Casimir effect also provided something else, a bridge between the very small and the very large. On the microscopic scale, the Casimir force arises from the quantum fluctuations of fields. But those same fluctuations exist everywhere, at every point in the cosmos. If they can move plates in a laboratory, could they also influence the behavior of the universe itself? This question would soon become central to cosmology. The vacuum was no longer just a feature of quantum mechanics. It was a player in the fate of the cosmos. The experiments also highlighted the extraordinary precision of quantum theory. The Casimir force matched the predictions of quantum electrodynamics with remarkable accuracy. Every refinement in measurement confirmed the same truth: the vacuum is alive. There was no escaping the conclusion. The absence of matter is still something, and that something is restless, powerful, and universal. The vacuum is not an empty stage for reality. It is part of the cast. For engineers and technologists, the Casimir effect presented both challenges and opportunities. In the realm of nanotechnology, where devices are built at scales only a few hundred atoms wide, Casimir forces cannot be ignored. They can cause tiny moving parts to stick together, a problem known as stiction, or they can be harnessed to create new forms of actuation. What began as a question about philosophy and physics became a practical issue in the design of modern technology. The vacuum, once abstract, had become a tool. The philosophical impact was no less dramatic. The Casimir effect confirmed that nothingness is not nothing, but a field of possibility. The absence of visible particles does not mean absence of reality. Instead, it means a hidden activity beyond perception, a background that is always present. For human beings who had long imagined emptiness as a void to be feared, this was a revelation. Nothingness was not a threat to existence, but the foundation of it. As the 20th century gave way to the 21st, the Casimir effect stood as one of the clearest proofs of the quantum vacuum. It was not just a prediction, but a reality. It had been measured, confirmed, and explored in detail. The vacuum, once denied and dismissed, had proven itself to be alive with energy. The illusion of emptiness was gone, replaced by the recognition that what seems silent is filled with hidden power. The next step would be to carry this lesson from the laboratory to the cosmos. If vacuum fluctuations can move plates and shift atoms, what might they do on the scale of galaxies and universes? Could the same restless energy explain why the expansion of the universe is accelerating? Could it hold the key to dark energy, one of the greatest mysteries in modern science? These questions would soon propel physics into a new chapter, where the invisible power of empty space was revealed not just in the lab, but across the heavens. The Casimir effect had proven in the laboratory what theory had long suggested. The vacuum is alive with hidden activity. But the question remained, what exactly is this restless energy, and how deep does it go? To answer this, physicists turn to the concept of zero-point energy, the lowest possible energy that a quantum system can have. It is a strange idea, one that defies classical expectations. In the quantum world, even at absolute zero temperature, when all thermal motion has been removed, a system still possesses energy. This irreducible remainder is called zero-point energy, and it is one of the most astonishing discoveries of modern physics. The concept emerges directly from the uncertainty principle. In classical physics, a particle at rest is truly at rest. If it has no energy, it simply sits motionless. But in quantum mechanics, this is not allowed. The uncertainty principle dictates that certain pairs of properties cannot both be known with complete precision. Position and momentum are one such pair. If a particle were to be completely motionless, its momentum would be known exactly. That would violate the uncertainty principle. Therefore, even at its lowest energy, a particle must retain some motion. It must jitter, vibrate, or fluctuate. This motion is not optional. It is built into the structure of reality. This is why zero-point energy is so profound. It means that the idea of perfect stillness does not exist in nature. Atoms, molecules, and even entire fields cannot be completely frozen. They always retain some energy, even in their ground state. This realization overturned the classical vision of absolute zero. In the 19th century, physicists believed that if a substance were cooled to absolute zero temperature, all motion would cease. But quantum mechanics showed that this is impossible. The lowest temperature is not the end of motion, but the beginning of a new kind of motion: zero-point motion. One of the most striking examples of zero-point energy is found in liquid helium. When helium is cooled down, it refuses to freeze into a solid even at temperatures near absolute zero. Instead, it remains liquid, a behavior unique among elements. The reason is that the helium atoms retain so much zero-point energy that they cannot be locked into a crystalline structure. They continue to move even when all thermal energy has been removed. This restless motion keeps helium fluid when every other element would have frozen. It is a vivid reminder that quantum mechanics does not allow true stillness. Zero-point energy is not limited to exotic substances. It affects every atom and molecule in existence. Electrons in atoms retain zero-point motion that determines the size of their orbitals. Molecules vibrate with zero-point energy that influences their chemical properties. The very structure of matter depends on it. Without zero-point energy, atoms would collapse inward, molecules would behave differently, and the stability of matter as we know it would vanish. Zero-point energy is not a small correction. It is essential to the existence of the world. Physicists soon realized that this principle applies not only to individual particles or atoms, but to fields themselves. Every quantum field, whether it is the electromagnetic field or the electron field, has a ground state that contains zero-point energy. The universe is filled with these fields, and each contributes to the restless background of reality. This means that the vacuum, the supposed emptiness of space, is saturated with zero-point energy. It is everywhere, in every direction, at every scale. The quiet between galaxies is not silent. It hums with the energy of the fields. This realization was unsettling, because it meant that empty space holds an immense amount of energy. The exact amount depends on how the calculation is done, but the numbers are staggering. If all the zero-point energy of the vacuum could somehow be tapped, the amount of power contained in even a small volume of space would be enormous, far beyond anything we could imagine. In practice, the laws of physics prevent us from extracting this energy, but its presence cannot be denied. The vacuum is not a void, but a vast reservoir of hidden power. For philosophers, this was another reversal. Nothingness had once been imagined as absence, then redefined as structure, and now revealed as abundance. Zero-point energy meant that even in the absence of particles, even at the lowest temperature, reality was never empty. There was always something, always energy, always activity. The concept of nothing had been erased from physics. In its place stood a universe in which emptiness is full and stillness is impossible. The recognition of zero-point energy deepened the mystery of the cosmos. If the vacuum is alive with this hidden energy, what role does it play in the universe as a whole? Could it influence cosmic evolution, the expansion of space, or the fate of time itself? These questions would soon drive physicists to connect the smallest scales of quantum mechanics with the largest scales of cosmology. But before that, the concept of zero-point energy had to be explored and understood in its own right. It was not just a theoretical curiosity. It was a window into the deepest truths of reality. The idea of zero-point energy is more than a theoretical curiosity. It is a reality that touches every aspect of the material world. At the atomic scale, zero-point motion shapes the very structure of matter. An electron orbiting the nucleus of an atom is not locked into a perfect path. Instead, it hovers in a cloud of probability, constantly jostled by fluctuations. Even at its lowest possible energy, the electron does not rest. It has a finite spread in space, a reminder of the uncertainty principle at work. Without this irreducible motion, atoms would collapse, electrons would spiral inward, and matter itself would vanish. Zero-point energy is the invisible scaffolding that keeps the atomic world stable. Molecules, too, are shaped by this restless energy. When two atoms bond to form a molecule, the bond is not rigid. The atoms vibrate around their equilibrium positions. These vibrations are not entirely thermal. Even if the molecule is cooled to near absolute zero, vibration continues. This residual motion is zero-point vibration, a permanent trembling built into the structure of the molecule. It influences how molecules absorb and emit radiation, how they react with one another, and how they store energy. Chemistry itself, the endless dance of reactions that makes up life, depends on zero-point energy. One of the clearest ways to appreciate the role of zero-point motion is to consider liquid helium again. Unlike other substances, helium remains liquid all the way down to absolute zero temperature under normal pressure. The explanation lies in the quantum nature of helium atoms. They are so light and interact so weakly that their zero-point motion dominates. Even when thermal energy is removed, the atoms still move too vigorously to settle into a crystalline lattice. They remain fluid, a striking demonstration of quantum restlessness at the macroscopic scale. This phenomenon astonished scientists when it was first discovered, and it continues to be one of the most vivid proofs that zero-point energy is real. Helium also exhibits another extraordinary behavior at low temperatures. It becomes a superfluid. In this state, it flows without viscosity, able to climb the walls of containers and creep through the tiniest cracks. Superfluidity is a macroscopic quantum phenomenon, made possible by the persistence of zero-point motion. It shows that the consequences of quantum mechanics are not confined to the microscopic world, but can emerge on human scales. When physicists observe helium flowing endlessly in a closed loop without slowing, they are seeing zero-point energy at work in one of its most dramatic forms. But zero-point energy is not only about exotic elements at cryogenic temperatures, it influences the ordinary world too. Vibrations in crystals, known as phonons, retain zero-point motion that affects their thermal and electrical properties. The stiffness of materials, the way they conduct heat, and the way they respond to light are all influenced by zero-point vibrations. In fact, without zero-point energy, many of the properties of solids and liquids would change dramatically. The stable world of everyday experience is underpinned by the restless motion of the quantum world. For a long time, physicists wondered whether zero-point energy might also manifest in radiation fields. The electromagnetic field, even in its lowest energy state, should contain fluctuations. This idea was tested in experiments like the Lamb shift and the Casimir effect, both of which revealed the fingerprints of zero-point energy in action. These effects showed that radiation fields too cannot be perfectly still. They always carry a baseline of activity, an irreducible hum that shapes how matter interacts with light. The recognition of zero-point energy challenged the idea of absolute zero in profound ways. In classical thermodynamics, absolute zero was imagined as the ultimate endpoint, a state of perfect stillness. But quantum mechanics showed that such stillness does not exist. Even at zero temperature, atoms vibrate, molecules tremble, and fields fluctuate. Absolute zero is not a place where motion ends, but a place where motion takes on its most subtle form. The laws of physics forbid stillness. The universe itself never rests. This truth carried philosophical weight as well. For centuries, nothingness had been imagined as silence, as stillness, as absence. But zero-point energy showed that stillness is impossible. The ground of reality is restless. The foundation of existence is activity. Even when stripped of all heat, all light, all matter, the universe retains energy. Nothing is never truly nothing. This realization reshaped not only physics, but the very human understanding of being. The implications of zero-point energy extend far beyond atoms and molecules. If every system retains this irreducible energy, and if every field contributes to it, then the vacuum itself must be saturated with zero-point energy. The amount contained in even a small volume of space is staggering. Though it cannot be extracted in any simple way, its presence may play a role in shaping the cosmos. As scientists probed deeper into this mystery, they began to suspect that zero-point energy could connect the smallest scales of quantum mechanics to the largest scales of cosmology. The restless ground state of the vacuum might not only influence atoms, but determine the fate of the universe itself. The reality of zero-point energy became most striking when scientists considered radiation itself. In classical physics, a field of light or electromagnetic radiation could, in principle, be reduced to nothing. If all photons were removed, the field would be silent. But quantum theory revealed that even in the absence of photons, the electromagnetic field retains fluctuations. It has zero-point energy. This was not just a mathematical curiosity, but something that could be tested, and the results changed physics forever. One of the clearest demonstrations was the Lamb shift. The tiny difference in energy levels in the hydrogen atom, discovered in 1947, could not be explained without the presence of electromagnetic vacuum fluctuations. The shift was a sign that the atom was not isolated, but surrounded by a restless field. Even when stripped of all visible radiation, the electromagnetic field remained alive. The electron felt it. The atom carried its imprint. The discovery proved that radiation itself has zero-point energy, and that the vacuum can never be silent. Another powerful example is the Casimir effect. The force between two metal plates arises directly from the suppression of zero-point fluctuations of the electromagnetic field between them. The energy outside the plates is slightly greater than inside, producing a measurable attraction. The Casimir effect is therefore not only a curiosity of quantum field theory, but also a direct proof of zero-point energy. It shows that the vacuum is structured by fluctuations that can be shifted and shaped, and that these fluctuations can produce forces strong enough to move matter. These demonstrations led physicists to a startling realization. Zero-point energy is not confined to isolated systems like atoms or molecules. It is everywhere. Every field, whether electromagnetic, electron, or quark, contributes its own zero-point energy. The combined effect fills all of space with an enormous background of hidden energy. Though invisible, it is real, and the scale of it is staggering. Calculations suggest that the density of zero-point energy in the vacuum is immense, far greater than the energy contained in ordinary matter. This raised a paradox. If the vacuum is filled with such vast energy, why does the universe not behave as though it is dominated by it? In principle, the gravitational effect of zero-point energy should be enormous, enough to curve space and crush the cosmos. Yet the universe is not collapsing. This tension between theory and observation became known as the cosmological constant problem, one of the greatest unsolved mysteries in physics. But even before that problem was fully recognized, physicists understood that zero-point energy was not just a detail of quantum theory. It was a window into the deepest questions of cosmology. Meanwhile, in the laboratory, physicists continued to explore the consequences of zero-point energy. They discovered that it could influence not only atoms, but entire systems of matter. Vibrations in crystals, stability in molecules, and even the noise in electronic circuits could be traced to the restless fluctuations of the vacuum. Engineers working with superconductors and quantum devices learned to account for zero-point energy in their designs. The invisible background of the vacuum had practical consequences. It was no longer confined to philosophy or theory. It was shaping the world of technology. This connection between quantum physics and practical technology opened new possibilities. In the field of quantum optics, scientists began to exploit vacuum fluctuations to create phenomena such as squeezed light, where the uncertainty in one property of light is reduced at the expense of another. These techniques, born from the recognition of zero-point fluctuations, are now used in applications as precise as gravitational wave detectors. The restless vacuum, once imagined as absence, became a tool for probing the universe. Zero-point energy also plays a role in quantum information science. In superconducting circuits, the noise produced by vacuum fluctuations can limit performance, but the same fluctuations can also be manipulated to stabilize quantum states. The fact that nothingness can be engineered and shaped is one of the most surprising twists of modern physics. The vacuum is no longer just a background. It is a medium that can be designed. Yet the greatest mystery of zero-point energy lies not in technology, but in cosmology. If every field contributes energy to the vacuum, then the universe is permeated with a vast and invisible reservoir of power. Could this be connected to dark energy, the mysterious force driving the accelerating expansion of the cosmos? Could the fate of the universe itself be tied to the restless energy of what we once called nothing? These questions transformed zero-point energy from a curiosity into one of the central puzzles of science. The recognition of zero-point energy was a profound turning point. It shattered the classical vision of stillness and replaced it with a universe that never rests. It revealed that emptiness is an illusion, that silence hides a symphony, and that even absence is a kind of presence. It connected the smallest scales of quantum mechanics with the larger scales of cosmology. It showed that the vacuum is not a void, but a foundation, not silence, but hidden music, not nothing but everything. Zero-point energy revealed that the vacuum is not a passive background, but a restless foundation on which all of reality is built. From the trembling of electrons in atoms to the Casimir force between metal plates, from the vibrations of molecules to the refusal of helium to freeze, the evidence is overwhelming. The universe does not permit stillness. The ground state of existence is always alive. This realization reshaped not only physics, but the human understanding of nothingness itself. What makes zero-point energy so astonishing is its universality. It is not confined to one substance, one field, or one corner of nature. It is everywhere. Every quantum system, whether large or small, retains energy even in its lowest state. This truth applies to atoms, molecules, fields, and the very fabric of space. No region of the cosmos is exempt. Even in the most remote intergalactic voids, where a few lonely atoms drift across millions of light years, the vacuum is saturated with zero-point energy. The emptiest parts of the universe are still full. This truth challenged long-held ideas about the limits of physics. Classical science had imagined that if you removed all heat, all matter, and all radiation, what remained would be nothing. Quantum mechanics replaced that vision with a new one. Even when stripped of everything we can see, the universe still hums with invisible activity. The lowest energy state is not zero, but a constant vibration, a whisper of existence that can never be silenced. This is not a defect of the theory, but a fundamental property of reality. For technology, zero-point energy became both a challenge and an opportunity. In nanotechnology and quantum computing, vacuum fluctuations can create noise that limits performance. Yet the same fluctuations can also be manipulated and controlled. Engineers learned to design systems that either minimize or exploit zero-point effects. Quantum optics, superconducting circuits, and ultra-sensitive detectors all rely on the restless activity of the vacuum. The fact that nothing can be engineered has become one of the great surprises of the modern age. But the implications go far beyond technology. They reach into the deepest questions of cosmology. If the vacuum is filled with zero-point energy, then its gravitational effect should influence the expansion of the universe. For decades, this was treated as a theoretical curiosity, a strange implication of quantum field theory. But in 1998, observations of distant supernovae revealed that the expansion of the universe is accelerating. The cosmos is not slowing down under the pull of gravity, but speeding up, driven by a mysterious force. Many physicists believe that this force is a manifestation of vacuum energy, zero-point energy on the scale of the universe. This connection between the smallest scales of quantum mechanics and the largest scales of cosmology is one of the most profound in science. It means that the restless motion of electrons in atoms, the vibrations of molecules, and the forces between plates in a laboratory are all connected to the fate of galaxies, stars, and time itself. The same principle that keeps helium fluid at absolute zero may be driving the expansion of the cosmos. Zero-point energy is not just a detail of physics, it is a key to the universe. The recognition of this truth raises profound questions. Why does the vacuum contain energy? Why is the amount of energy it holds so different from what theory predicts? How can the same fluctuations that shape atoms also shape the destiny of space and time? These questions form the heart of modern physics. They show that zero-point energy is not only an established fact, but also a mystery that points toward new discoveries. Philosophers once debated whether nothing could exist. Modern physics has answered with a resounding no. Nothingness is impossible. The vacuum is always something, always alive, always filled with zero-point energy. This truth erases the boundary between being and non-being. It shows that absence is a kind of presence, that stillness is an illusion, and that silence hides a symphony. The human search for nothing has revealed instead a foundation richer than anything imagined. As the 20th century closed and the 21st began, the concept of zero-point energy stood at the center of both physics and philosophy. It explained the behavior of matter, the structure of atoms, and the phenomena of the laboratory. It hinted at the forces shaping the expansion of the universe, and it reminded humanity that the deepest truths often hide in what seems simplest. The story of zero-point energy is not only a chapter in science, but a turning point in our understanding of existence itself. The next step in this journey would be to follow the implications of vacuum energy to the scale of the cosmos. If the vacuum is alive with zero-point energy, then the universe itself is shaped by it. From Einstein's cosmological constant to the discovery of cosmic acceleration, the restless energy of nothing defines the destiny of everything. The stage was set for the next great revelation, in which the vacuum would step out of the laboratory and reveal its power in the heavens. The discovery of zero-point energy in the quantum world was already astonishing. But what if the same restless activity of the vacuum extended its influence across the entire cosmos? Could the invisible hum of empty space shape the destiny of galaxies, stars, and time itself? This possibility began to emerge in the early 20th century, long before anyone had measured the Casimir effect or the Lamb shift. It was first suggested by Albert Einstein himself, though in a way he could not have anticipated. In 1917, Einstein applied his theory of general relativity to the universe as a whole. Relativity described how mass and energy curve space, and how this curvature governs the motion of matter. When Einstein wrote down the equations of cosmology, he faced a problem. His equations predicted a dynamic universe, one that either expanded or contracted under the influence of gravity. But at the time, most scientists assumed that the universe was static and eternal. To force his equations to allow a static universe, Einstein introduced an additional term, a repulsive factor he called the cosmological constant. The cosmological constant acted like a kind of anti-gravity. It supplied a repulsive pressure that balanced the attractive pull of gravity, keeping the universe from collapsing. Einstein did not think of it as vacuum energy. At the time, the quantum theory of fields was still in its infancy, and the concept of zero-point fluctuations had not yet been connected to cosmology. For him, it was simply a mathematical trick, a constant added to the equations to produce the result he wanted. A little more than a decade later, Edwin Hubble discovered that galaxies are receding from one another, proving that the universe is expanding. Einstein realized that his assumption of a static universe was wrong. Legend has it that he called the cosmological constant his greatest blunder, though historians debate whether he ever used those exact words. Regardless, he abandoned the idea, believing it unnecessary in an expanding cosmos. For much of the 20th century, the cosmological constant was forgotten, an odd relic of an earlier misunderstanding. But the story did not end there. As quantum field theory developed, physicists realized that the vacuum itself contained energy. Zero-point energy, present in every field, should contribute a uniform energy density that fills all of space. And the effect of such energy, when inserted into Einstein's equations, would look exactly like a cosmological constant. It would create a repulsive pressure that pushes the universe apart. Suddenly, Einstein's discarded term looked less like a blunder and more like a prophecy. For decades, this connection remained speculative. No one knew whether the vacuum energy was real on cosmic scales. It was easy to see its effects in atoms, molecules, and laboratory experiments, but the universe is vast, and other forces could dominate. Yet the mathematics was compelling. If vacuum energy existed, it should act as a uniform pressure spread evenly across space, influencing the expansion of the cosmos. It would be invisible but powerful, subtle yet inescapable. The breakthrough came in the late 1990s when two teams of astronomers set out to measure the expansion of the universe using distant supernovae. These exploding stars act as cosmic mile markers, their brightness revealing their distances. By comparing the apparent brightness of supernovae with their redshifts, the teams could trace the history of cosmic expansion. They expected to find that the universe was slowing down under the pull of gravity. Instead, they found the opposite. The expansion was accelerating. Galaxies were being pushed apart faster and faster as time went on. This discovery stunned the scientific community. It implied that some mysterious force was acting against gravity, driving cosmic acceleration. The simplest explanation was Einstein's cosmological constant, or in modern terms, vacuum energy. The restless fluctuations of empty space, negligible on human scales, seemed to dominate the universe on cosmic scales. What had been dismissed as a mathematical curiosity had returned as the leading candidate to explain the fate of the cosmos. The discovery of accelerating expansion in 1998 was awarded the Nobel Prize in Physics in 2011. It transformed cosmology overnight. Dark energy, as the mysterious force came to be called, became one of the central puzzles of modern science. And the most natural interpretation of dark energy was the energy of the vacuum itself. Zero-point fluctuations, present everywhere, were not just shaping atoms, they were shaping the universe. The discovery of cosmic acceleration was one of the most surprising moments in the history of astronomy. For decades, scientists had assumed that the expansion of the universe must be slowing down. Gravity, pulling on every galaxy and every star, should gradually reduce the rate of expansion. The only debate was whether the expansion would eventually halt and reverse in a collapse, or whether it would continue forever at a slower and slower pace. The idea that expansion could be speeding up was unthinkable, yet the supernova data made the conclusion unavoidable. Something was pushing the cosmos apart. This invisible force was soon called dark energy. The name captured the mystery. It was dark because it could not be seen, and it was energy because it seemed to act as a background field driving the acceleration. The simplest explanation for dark energy was that it was vacuum energy, the uniform zero-point energy of space itself. Quantum field theory predicted that the vacuum should have energy, and general relativity showed that such energy would act as a repulsive pressure. In this way, two of the most successful theories in physics pointed toward the same idea. Measurements confirmed that dark energy is not a minor player. Today, observations of the cosmic microwave background, galaxy surveys, and supernova studies all point to the same conclusion. About 70% of the total energy content of the universe is in the form of dark energy. Matter, both visible and dark, makes up only about 30%, and radiation contributes less than 1%. This means that the fate of the universe is dominated not by stars, galaxies, or even dark matter, but by the energy of empty space. The vacuum, once dismissed as nothing, is the largest component of everything. The influence of dark energy is subtle on small scales, but overwhelming on large ones. Within galaxies and clusters, gravity dominates, binding stars and matter together. But across billions of light years, the repulsive effect of vacuum energy accumulates, steadily accelerating the expansion. The farther galaxies are from one another, the more vacuum energy dominates their motion. This is why the discovery of acceleration was only possible by looking at distant supernova. The effect is invisible in our neighborhood, but clear when measured across cosmic distances. Astronomers continue to refine their measurements of dark energy. Projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and space missions such as the European Space Agency's Euclid Telescope and NASA's upcoming Roman Space Telescope are designed to map the expansion of the universe with increasing precision. They measure not only the rate of acceleration, but also whether it changes over time. If dark energy is truly vacuum energy, it should remain constant, unchanging as the universe evolves. If it varies, then it may point to new physics beyond our current theories. The interpretation of dark energy as vacuum energy is appealing because it fits naturally into existing physics. Quantum field theory says that every field has zero-point energy, and general relativity says that such energy produces a repulsive effect. When combined, these ideas describe a universe in which empty space drives cosmic expansion. In this view, the vacuum is not merely the stage on which cosmic events unfold, but the engine powering the expansion of the cosmos. Yet the scale of this influence is humbling. Galaxies, stars, and planets, the structures we see and touch, are the minority. The vast majority of the universe is invisible and untouchable. It is energy that exists not in particles, but in the fabric of space itself. For human beings who once thought the Earth was the center of creation, this is another in a long series of humbling truths. We live not in a universe dominated by matter, but in one ruled by the invisible energy of the vacuum. This realization carried philosophical weight as well. The concept of nothingness had been turned inside out. What we once called empty space is not empty, but full. It is the dominant reality of the cosmos, the unseen presence that dictates the fate of galaxies. Nothing is not only something, it is everything. The silence of space is louder than the roar of stars. The recognition of vacuum energy as the leading candidate for dark energy set the stage for a new era of physics. But it also raised a troubling question. When physicists tried to calculate the amount of vacuum energy from quantum field theory, the results did not match the observed value. In fact, they were not just a little off, but catastrophically wrong. Theory predicted a vacuum energy density so enormous that the universe should not exist in its current form. The difference between prediction and observation was staggering, a mismatch of more than 100 orders of magnitude. This became known as the cosmological constant problem, the worst prediction in the history of physics. The discovery that vacuum energy could explain dark energy brought excitement, but it also opened a problem so vast that some called it the greatest puzzle in science. Quantum field theory, the framework that had successfully explained the behavior of particles, predicted that the vacuum should be brimming with energy. Each quantum field contributes to this background, and when summed across all known fields, the calculated energy density is mind-bending. The numbers are so large that, if correct, the universe would be torn apart by the overwhelming repulsion. Yet the observed expansion tells a different story. The actual vacuum energy is tiny in comparison, just enough to accelerate the universe, but not enough to destroy it. Physicists faced a mismatch of staggering proportions. Calculations suggested that the vacuum energy should be about 10 to the power of 120 times larger than the observed value. To put that into perspective, this is like predicting the weight of an apple and instead getting a number larger than the mass of the universe. It is not simply an error, it is the worst discrepancy between theory and experiment in the history of physics. This became known as the cosmological constant problem. Why is the predicted vacuum energy so much larger than the observed? One possibility is that our calculations are missing something fundamental. Perhaps the contributions from different fields somehow cancel one another, leaving only a tiny remainder. But no known mechanism explains such a delicate balance. Another possibility is that the theory itself is incomplete, and that a deeper framework beyond quantum field theory and general relativity is required. This is one of the reasons physicists search for a theory of quantum gravity, a unification of the smallest and largest scales of nature. The cosmological constant problem may be the clue that points the way. Despite the mystery, the evidence for dark energy remains overwhelming. Observations of supernovae, the cosmic microwave background, and the distribution of galaxies all point to the same conclusion. The universe is expanding at an accelerating rate, and about 70% of its energy content is in this mysterious form. Whether it is truly vacuum energy or something even stranger, dark energy is real. It is the dominant force shaping the future of the cosmos. For cosmologists, the presence of dark energy changes everything. In the past, the fate of the universe was thought to depend on the balance between matter and gravity. If there was enough matter, gravity would eventually slow expansion and cause a collapse. If there was not enough, the universe would expand forever, but gradually slow down. Dark energy changed that picture. If vacuum energy remains constant, then the expansion will not only continue, but accelerate without end. Galaxies will drift farther apart, stars will burn out, and the universe will fade into a cold and empty darkness. The possibility that the fate of everything depends on vacuum energy adds a dramatic twist to the human story. What was once dismissed as nothing is now seen as the driver of cosmic destiny. Every galaxy, every star, every planet is subject to the invisible push of empty space. The silence of the vacuum shapes not only atoms and laboratory experiments, but the future of the universe itself. This recognition deepened the philosophical weight of the discovery. It forced scientists and philosophers alike to reconsider the meaning of nothingness. Empty space, once thought to be the simplest of all concepts, turned out to be the most complex. It is not an absence, but a presence. Not silence, but hidden music. Not void, but energy. The vacuum is not only alive, but also powerful enough to decide the fate of time. And yet, for all its power, vacuum energy remains a mystery. Why is its value so small compared to theoretical predictions? Why is it not exactly zero if cancellations do occur? Why does it exist at all? These questions remain unanswered, standing as some of the greatest challenges in modern physics. The cosmological constant problem is not just a puzzle for specialists. It is a clue that reality is deeper than we understand, that the laws of physics are not yet complete. The recognition that vacuum energy may be driving the expansion of the universe transformed cosmology into a story of tension between gravity and emptiness. Gravity pulls matter together, shaping stars, galaxies, and clusters. Vacuum energy pushes outward, stretching the fabric of space itself. The contest between these two forces is not balanced. On small scales, gravity wins, binding planets to stars and stars to galaxies. But across the cosmos, over billions of light years, the push of vacuum energy dominates. It is not matter, but emptiness that rules the universe. The future depends on whether vacuum energy remains constant. If it is truly the cosmological constant, then its value will not change over time. In that case, the acceleration of the universe will continue forever. Galaxies will move farther and farther apart until distant galaxies vanish from sight. In trillions of years, only the stars of our own local group of galaxies will remain visible. As stars burn out and black holes slowly evaporate, the cosmos will drift toward a state of eternal darkness and silence. The universe would end not with a bang, but with a slow fade into nothingness, a heat death driven by the vacuum itself. If vacuum energy is not constant but evolves with time, the possibilities are even stranger. If it grows stronger, the expansion could accelerate so rapidly that galaxies, stars, planets, and even atoms are torn apart in a cosmic catastrophe known as the Big Rip. If it weakens, the universe might slow and perhaps collapse in a new Big Crunch. These scenarios depend on the nature of dark energy, whether it is truly vacuum energy or some dynamic field that changes with time. The uncertainty is profound. The destiny of everything hangs on the properties of what we call nothing. The discovery of accelerating expansion forced cosmologists to reimagine the entire history of the universe. In the early moments after the Big Bang, matter and radiation dominated. Galaxies formed, stars ignited, and cosmic structure took shape under the pull of gravity. But as the universe expanded, the density of matter thinned, while the density of vacuum energy remained constant. Eventually, vacuum energy became dominant and acceleration began. We live in that era now, when emptiness outweighs matter and dictates the cosmic future. The reign of galaxies is temporary. The reign of the vacuum may be eternal. This perspective is humbling. For thousands of years, human beings debated the meaning of nothingness, imagining it as absence, silence, or void. Now science shows that nothing is the most powerful something of all. It governs the expansion of the cosmos. It shapes the fate of galaxies. It holds the key to time itself. The emptiness between stars is not absence, but the very engine of the universe. Yet the mystery of its value remains unsolved. The tiny number measured by cosmologists does not match the enormous predictions of quantum theory. The mismatch is so extreme that it points to new physics, a deeper truth beyond what we know. The cosmological constant problem, as it is called, is more than a puzzle. It is a signpost. It tells us that our understanding of reality is incomplete, that the true nature of the vacuum has yet to be revealed. As this chapter closes, the story of vacuum energy stands at a crossroads. On one side, it explains the accelerating universe, the dominance of dark energy, and the fate of time itself. On the other side, it presents the greatest mismatch between theory and observation in all of science. The vacuum is at once the solution and the problem, the simplest explanation and the deepest mystery. The journey continues in the next chapter, where the full weight of the cosmological constant problem will be explored. It is a problem so vast that it challenges the foundations of physics, one that forces us to confront the limits of our knowledge and the possibility of new frameworks for reality. The invisible power of empty space, proven in the lab and measured in the heavens, now reveals its paradox. The vacuum, which seemed to promise answers, presents instead the greatest riddle of all. By the late 20th century, physicists had reached a sobering realization. The same vacuum energy that explained the acceleration of the universe also presented the greatest mismatch between theory and observation in the history of science. Quantum field theory, the framework that describes particles and their interactions, predicted that the vacuum should contain an enormous energy density. Yet astronomical measurements showed that the actual value was tiny by comparison. The difference was not a factor of 2, or 10, or even 1,000. It was a factor of 10 to the power of 120. No other area of science had ever produced a gap so extreme. This became known as the cosmological constant problem. The heart of the problem lies in the way quantum field theory treats zero-point energy. Every quantum field contributes a baseline amount of energy to the vacuum. The electromagnetic field has zero-point fluctuations. So do the electron field, the quark fields, the gluon field, and all others. Each field, at every possible mode or frequency, adds its contribution. When summed across all the fields of nature, the result is enormous. The vacuum, according to these calculations, should be saturated with energy dense enough to curve space so violently that the universe would either collapse instantly or expand at an unimaginable rate. Of course, this is not what we observe. The universe exists. Galaxies form, stars shine, and the cosmic expansion proceeds at a gentle acceleration. The observed vacuum energy is small, large enough to drive cosmic acceleration, but tiny compared to theoretical predictions. The question is why? What cancels the enormous contributions predicted by theory, leaving only a faint residue? Why is the cosmological constant not zero, but not enormous either? This tension sits at the very heart of physics. Some physicists hope that the problem might be solved by cancellations. Perhaps the contributions of different fields offset one another, like positive and negative terms in a complex equation. Supersymmetry, a proposed extension of the standard model of particle physics, suggested that for every particle, there should be a partner particle. In such a theory, the zero-point energy of particles and their partners could cancel, greatly reducing the vacuum energy. But experiments have not yet found evidence for supersymmetric particles, and even if they exist, the cancellation is not perfect. The problem would remain. Others speculated that some new principle of physics might set the vacuum energy to zero exactly, but this idea ran into its own difficulty. Observations show that the vacuum energy is not zero. It is small, but it is real. It drives the accelerating expansion of the universe. So the challenge is not to explain why the cosmological constant vanishes, but why it has the small, non-zero value we measure. This is sometimes called the fine-tuning problem. The value of vacuum energy appears to be finely tuned to allow galaxies, stars, planets, and life itself to exist. A little more, and the universe would expand too quickly for structure to form. A little less, and it would collapse too soon. This fine-tuning strikes many scientists as suspicious. It suggests that something deeper is at work. Some have proposed that the solution might lie in the multiverse, the idea that our universe is only one among many. In such a picture, different universes could have different values of vacuum energy. We live in one where the value happens to be small enough to allow life. This is known as the anthropic principle. We observe the universe to be the way it is because otherwise we would not be here to observe it. Though controversial, this idea has gained attention because no conventional calculation explains the smallness of the cosmological constant. The cosmological constant problem is not only a puzzle of numbers, it is a clue that our understanding of the relationship between quantum mechanics and gravity is incomplete. Quantum field theory and general relativity are both extraordinarily successful, but they remain ununified. When we try to combine them to calculate vacuum energy, the result is nonsense. The mismatch of 10 to the power of 120 is not just a mistake, it is a signpost pointing toward new physics. It suggests that the ultimate theory of nature, whatever it is, must explain why the vacuum has the energy it does. This problem is sometimes called the most embarrassing failure of theoretical physics. For decades, physicists had prided themselves on the precision of quantum electrodynamics, which matched experiments to more than 10 decimal places. Yet when the same framework was applied to the vacuum, it produced an error so vast it defied comprehension. The cosmological constant problem is a reminder that success in one domain does not guarantee understanding in another. It is a humbling lesson that the universe is deeper and stranger than our theories can yet capture. Physicists have never been comfortable with the enormous mismatch between theory and observation. The cosmological constant problem is not just a numerical error, it is a wound in the heart of physics, a reminder that the two most successful theories we have, quantum field theory and general relativity, do not fit neatly together. Over the years, many ideas have been proposed to explain the paradox, but none has fully succeeded. One of the earliest hopes was that some hidden symmetry in nature might force the vacuum energy to cancel out. Symmetry has often been the guiding light of physics. The conservation of energy arises from the symmetry of time. The conservation of momentum arises from the symmetry of space. It seemed natural to think that some deeper symmetry might protect the universe from the catastrophic effects of vacuum energy. Supersymmetry was the leading candidate. In a supersymmetric universe, every particle has a partner. The electron would have a selectron, the photon a photino, the quark a squark. The zero-point contributions of particles and their superpartners would cancel, leaving behind a much smaller vacuum energy. This was an elegant solution, but experiments have not yet found evidence for supersymmetry. Particle accelerators, like the Large Hadron Collider, have searched for superpartners in vain. Even if supersymmetry exists at higher energies, the cancellation is not exact. The cosmological constant problem remains, only slightly softened. Another idea was that some as yet undiscovered law of physics forces the cosmological constant to be exactly zero. This would be satisfying, as it would remove the fine-tuning problem entirely. But nature refuses to cooperate. Observations show that the vacuum energy is not zero. It is small, but positive, driving the accelerating expansion of the universe. Any solution must explain not just why the vacuum energy is not huge, but also why it is not nothing. This is a more subtle and difficult challenge. Some physicists turn to the idea of quintessence, a dynamic form of dark energy. Instead of a fixed cosmological constant, quintessence imagines a field that evolves with time, slowly changing as the universe expands. This could explain why the observed value is small today, while avoiding the worst predictions of quantum field theory. But no clear evidence for quintessence has been found. All measurements so far are consistent with a simple, constant vacuum energy. Perhaps the boldest proposal is that the vacuum energy is not determined by physics alone, but by selection. This is the anthropic principle, linked to the idea of a multiverse. If there are many universes, each with different values of vacuum energy, then most would be uninhabitable. In universes where the vacuum energy is too large, galaxies could never form. In universes where it is too negative, space would collapse quickly. Life could only arise in universes with values close to the one we observe. We live in such a universe not because the vacuum energy had to be small, but because only in such a universe could we exist to notice it. This explanation is controversial. Many physicists dislike it because it seems to give up on finding a fundamental reason. It shifts the problem from physics to statistics, suggesting that we are simply in a lucky universe. And yet, in the absence of better answers, the anthropic principle has gained traction. It offers a way to make sense of the fine-tuning without requiring a new law of nature. Some even argue that it may be the only explanation possible. Meanwhile, cosmologists continue to probe the vacuum energy with increasing precision. Observations of distant galaxies, the cosmic microwave background, and gravitational lensing all confirm that dark energy behaves like a cosmological constant to within a few percent. If it varies, the change is too small to detect so far. The more precisely we measure, the more the universe looks like it is dominated by vacuum energy, and the more pressing the cosmological constant problem becomes. This puzzle highlights the unfinished state of physics. Quantum field theory explains the microcosm of particles. General relativity explains the macrocosm of gravity and space-time. But when we try to unite them in the vacuum, the theories clash. The result is a number so absurd it cannot be ignored. The cosmological constant problem is a signpost pointing toward the next revolution in science. It tells us that our picture of the vacuum, and perhaps our picture of reality itself, is incomplete. As the magnitude of the cosmological constant problem became clear, many physicists came to believe that its resolution would require a new framework of physics altogether. The clash between quantum field theory and general relativity is most severe when applied to the vacuum. And this suggests that the solution may lie in a unified theory that merges the two. For decades, efforts to create such a theory have focused on quantum gravity, the attempt to describe space-time itself in quantum terms. One promising candidate is string theory. In string theory, the fundamental building blocks of nature are not point particles, but tiny, vibrating strings. Different vibrations correspond to different particles, from electrons to quarks to photons. String theory naturally includes gravity, as one of its vibrational modes is a particle that behaves like the graviton, the hypothetical quantum of gravity. This gave hope that string theory could explain not only the cosmological constant problem, but also the unification of all forces. Yet string theory has not provided a simple answer. Instead, it has revealed a vast landscape of possible solutions, each corresponding to a different configuration of extra dimensions and fields. In many of these solutions, the vacuum energy takes different values. Some are enormous, some are small, some are positive, some negative. This diversity has been called the string landscape, a nearly infinite variety of possible universes, each with its own laws. In this picture, our small vacuum energy could simply be one choice among countless possibilities, selected by the conditions that allow galaxies and life to exist. This interpretation ties back to the anthropic principle and the idea of the multiverse. If the string landscape is real, then the cosmological constant problem may not have a unique solution. Instead, it may be that all possible values exist in different universes, and we live in the one that permits observers. Some physicists find this unsatisfying as it moves the problem from physics to philosophy. Others see it as the only viable explanation, given the enormity of the mismatch. Beyond string theory, other approaches to quantum gravity also grapple with the vacuum. Loop quantum gravity, for example, attempts to quantize space-time itself, describing space as a network of discrete loops. This framework also raises questions about vacuum energy, but so far it has not provided a clear resolution to the cosmological constant problem. What it does suggest, however, is that the problem lies in our incomplete understanding of space-time itself. The vacuum is not an empty stage but a quantum structure, and only by understanding its true nature can we resolve the paradox. Some researchers suggest that the cosmological constant problem hints that our picture of energy itself is incomplete. In quantum field theory, energy is defined relative to a baseline. Perhaps the enormous numbers that appear in calculations are artifacts of this definition, and the true gravitational effect of the vacuum is something else entirely. This line of thought has led to creative proposals, but none have yet solved the puzzle in a way that satisfies both theory and observation. The persistence of the problem has had a profound effect on physics. It has humbled scientists, reminding them that even the most successful theories have limits. It has shifted attention to the vacuum as a central arena for discovery, not a background to be ignored. And it has inspired generations of researchers to search for a deeper understanding of reality. The fact that empty space contains the greatest mystery in science is a paradox that continues to drive the field forward. The cosmological constant problem is not just about numbers or equations, it is about the very structure of reality. It asks why the universe exists in its present form, why galaxies can form, why stars can shine, why life can arise. If the vacuum energy were much larger, the cosmos would be sterile. If it were smaller, it might collapse too quickly. The problem is not only scientific, but existential. It touches on the conditions that make our very existence possible. The cosmological constant problem stands as a reminder that our theories, for all their successes, are incomplete. Quantum field theory explains the microcosm with breathtaking precision. General relativity explains the macrocosm, the dance of stars and galaxies, with equal brilliance. But when they are brought together in the vacuum, their harmony breaks. The result is a prediction so wildly wrong that it cannot be ignored. This dissonance is not an accident. It is a clue. It tells us that the true theory of nature must be deeper than either framework alone. For many physicists, the vacuum has become the battleground where the next revolution in science will occur. In the past, revolutions arose when contradictions became too sharp to ignore. The failure of Newtonian mechanics to explain Mercury's orbit led to general relativity. The inability of classical physics to describe atoms led to quantum mechanics. Now the cosmological constant problem may be the contradiction that leads to the next great leap. The vacuum, once imagined as emptiness, may be the very key to unification. The paradox also carries profound philosophical weight. The vacuum energy appears finely tuned to a value that permits the existence of stars, galaxies, and life. If it were larger, structure could not form. If it were smaller or negative, the universe might collapse quickly. The fact that it takes the value we observe suggests either a deep principle we have not yet discovered, or a vast multiverse in which many values are possible. In either case, the problem forces us to confront the boundary between science and philosophy, between explanation and meaning. Some embrace the anthropic perspective, arguing that our universe is one of many, and that the cosmological constant is simply a selection effect. Others resist this view, convinced that a physical principle must exist to explain the smallness of the vacuum energy. The debate continues, and in the absence of experimental guidance, the problem remains open. Yet this uncertainty is itself a sign of progress. It keeps the question alive, ensuring that new generations of scientists will confront it with fresh ideas. The cosmological constant problem is sometimes described as the most pressing clue to the future of physics. If solved, it could open the door to a deeper understanding of space-time, gravity, and quantum fields. It could reveal the true nature of the vacuum, not as a background, but as the foundation of everything. It could connect the smallest scales of quantum mechanics with the largest scales of cosmology in a way that finally unifies them. The fact that the vacuum appears both simple and profoundly mysterious is what makes it so powerful a question. In practical terms, the problem continues to inspire new approaches. Physicists are exploring modifications to general relativity, models of evolving dark energy, and entirely new concepts of space and time. Experiments continue to refine the measurement of cosmic acceleration, searching for any hint that dark energy changes with time. If such a change were detected, it would revolutionize our understanding of the vacuum. If not, the mystery of why the vacuum energy has the value it does will only deepen. For humanity, the cosmological constant problem serves as a humbling reminder. What we once dismissed as nothing turns out to be the most important something of all. The emptiness between stars is filled with energy that determines the fate of the universe. And yet, our theories cannot explain it. The silence of the vacuum hides a riddle greater than any we have yet solved. As this chapter closes, the paradox remains. The vacuum energy is both the solution and the problem, the driver of cosmic acceleration and the greatest mismatch in physics. It is the invisible power that sustains the cosmos and the unanswered question that challenges our theories. It is a puzzle that forces us to look beyond the known, to imagine frameworks not yet discovered, to search for truths deeper than those we have. The journey now turns to another question. If the vacuum is so full of energy, can it be harnessed? Could humanity ever find a way to tap into this hidden reservoir? Science fiction has long dreamed of free energy drawn from the void, but the laws of physics impose limits, and the truth is stranger than the dream. The next chapter explores the possibility of harnessing the vacuum, separating fantasy from reality, and revealing what is truly possible in the restless sea of nothing. For as long as people have gazed at the stars and wondered about the universe, they have also dreamed of unlimited power. The discovery that empty space is filled with zero-point energy only fed this dream. If the vacuum is alive with energy, and if every cubic centimeter of space holds an unfathomable reservoir, then surely it must be possible to tap it. Could the endless energy of nothingness be harnessed to drive machines, power civilizations, or propel ships across the galaxy? This idea has fueled the imagination of scientists, inventors, and storytellers for more than a century. The appeal is easy to understand. Ordinary sources of energy, coal, oil, wind, sunlight, nuclear fuel, are limited. They require fuel or conditions that can be depleted or interrupted. The vacuum, by contrast, appears infinite. Space itself, stretching in every direction, is filled with zero-point fluctuations. The amount of energy predicted by quantum field theory, even allowing for the uncertainties in calculation, dwarfs anything humanity could hope to generate by conventional means. If it could be tapped, it would provide a power source beyond imagination. Science fiction writers have long seized on this vision. Stories have imagined spacecraft powered by the energy of the vacuum, cities running forever on nothing, and civilizations ascending to higher stages of existence through mastery of the void. In these tales, zero-point energy is portrayed as the ultimate energy source, limitless and free. It replaces fossil fuels, nuclear plants, and even stars themselves. The idea appeals because it transforms the most barren concept, emptiness, into the most fertile. What could be more poetic than drawing endless energy from nothing? In the mid-20th century, As the concepts of quantum mechanics and relativity spread into popular culture, the idea of harnessing zero-point energy took on new life. Some inventors claim to have built machines that could extract power from the vacuum. These claims, often promoted as free energy devices, captured the public imagination, but were never validated. No experiment has ever shown that usable energy can be drawn from zero-point fluctuations without violating the laws of physics. Yet the dream persisted, fueled by both genuine curiosity and the desire for a shortcut to infinite power. Physicists are quick to point out that the presence of zero-point energy does not mean it can be extracted. The energy is the ground state of the system, the lowest possible energy it can have. By definition, there is no lower state to drain into. To draw power from the vacuum would require pushing it into a still lower energy, but such a state does not exist. This is why attempts to use zero-point energy as a practical power source run into the same obstacle: conservation laws. You cannot extract energy from the ground state any more than you can build a perpetual motion machine. Still, the fascination continues. Some researchers have proposed creative ways to manipulate vacuum fluctuations without violating the laws of physics. One avenue of exploration is Casimir engineering, the deliberate design of materials and geometries to control Casimir forces. While this does not provide free energy, it could lead to nanoscale devices that harness the push and pull of the vacuum for practical use. In this way, the energy of nothingness might influence technology, not by fueling it directly, but by shaping the forces that govern it at the smallest scales. This subtle distinction is important. The vacuum is not an infinite power plant waiting to be tapped, but it is a medium that can be manipulated. Just as magnets cannot provide unlimited power, but can still be used in motors, generators, and countless devices, so too can the vacuum influence systems without being a fuel itself. The challenge is to understand how to work with vacuum fluctuations without expecting them to provide free energy. The dream of harnessing the vacuum reflects something deeper about humanity. It shows our refusal to accept limits, our longing for infinite horizons. Even if physics forbids drawing energy from nothing, the very act of imagining it has inspired creativity and exploration. It has forced scientists to test the boundaries of what is possible, to measure vacuum effects with ever greater precision, and to explore technologies that turn impossibility into innovation. The vacuum may not give us free energy, but it gives us something just as powerful: the drive to keep searching. The idea of drawing unlimited energy from the vacuum is tempting, but physics places strict boundaries on what is possible. The vacuum does indeed contain energy, but it is the lowest possible energy state, the ground state of all fields. By definition, a ground state has no lower state to fall into. This means that there is no way to siphon energy from it without breaking the fundamental laws of nature. In particular, the laws of thermodynamics and the conservation of energy prevent us from turning zero-point fluctuations into a perpetual power supply. The problem is not that the vacuum has no energy. Experiments like the Casimir effect prove that it does. The problem is that the energy is locked. Imagine a ball resting at the bottom of a valley. It cannot roll any lower because it is already at the minimum. Zero-point energy is like that ball. It vibrates, it fluctuates, it influences the world, but it cannot be tapped to do work in the conventional sense. To extract energy, there must be a higher state to fall from, but the ground state has none. Attempts to build so-called free energy machines often fail to recognize this. Over the past century, many inventors have claimed to design devices that capture energy from the vacuum. Some describe magnetic motors that supposedly run forever. Others point to exotic circuits that oscillate endlessly. None has ever stood up to scientific scrutiny. Careful tests show that they either rely on hidden power sources, measurement errors, or misunderstandings of quantum physics. The dream of breaking the laws of thermodynamics is as old as science itself, and it remains just that, a dream. Yet dismissing the possibility of free energy does not mean the vacuum is irrelevant to technology. The Casimir effect itself is proof that vacuum fluctuations can create measurable forces. While these forces cannot be used as a bottomless well of power, they can be engineered and controlled. This is the idea of Casimir engineering, designing surfaces and materials to harness vacuum forces in useful ways. For instance, at the nanoscale, where moving parts in microdevices can stick together due to Casimir attraction, researchers are exploring coatings and geometries that turn the vacuum from an obstacle into a tool. The same principle applies in quantum technologies. Quantum computers, sensors, and communication systems all interact with the vacuum in subtle ways. Zero-point fluctuations create noise that limits precision, but they also open possibilities. By manipulating quantum states of light, physicists have learned to reduce uncertainty in one property at the expense of another, creating what is called squeezed light. This technique, rooted in the restless activity of the vacuum, has become essential in detectors such as those used to observe gravitational waves. The hum of nothingness is being shaped to reveal cosmic ripples in space-time itself. Other areas of research look at how vacuum fluctuations influence superconductors and nanostructures. In superconducting circuits, which form the basis of many quantum computing platforms, vacuum noise must be carefully accounted for. It can destabilize fragile quantum states, but it can also be used creatively to probe and control them. The vacuum here is not a power source, but it is an environment that shapes what technology can achieve. By learning to live with the noise of emptiness, scientists are finding ways to use it. This is the crucial distinction. The vacuum cannot give us free energy, but it does interact with matter in powerful ways, just as we cannot drain a magnet for unlimited energy, but can still use magnetic forces in countless devices. So too can we use the vacuum's fluctuations in creative ways. Casimir forces, squeeze states, and quantum noise are not science fiction, but scientific realities. They remind us that the vacuum is not absence, but presence, and that presence has consequences. For philosophers, this has an almost poetic resonance. The void cannot be harvested like a mine, but it can be shaped, guided, and woven into the fabric of technology. The refusal of the vacuum to yield free energy is not a failure but a truth. It shows that the laws of physics have boundaries, and within those boundaries, creativity finds new paths. What was once imagined as emptiness is now a partner in discovery, shaping the limits and possibilities of science. The pursuit of harnessing the vacuum is not about breaking the rules, but about working with them. Free energy machines belong to fantasy. Real physics finds inspiration in subtle effects, in the way zero-point energy shifts atomic levels, bends mirrors, and hums through superconductors. The vacuum cannot be plundered, but it can be understood. And in that understanding, humanity finds not a bottomless well of power, but something just as valuable. A glimpse of the deep order of reality. The fascination with vacuum energy continues to inspire research at the edges of physics and engineering. While the dream of free energy remains impossible, the practical influence of the vacuum is undeniable. Nowhere is this clearer than in nanotechnology, where devices operate at scales so small that vacuum forces become significant. At distances of only a few nanometers, the Casimir effect can dominate, causing moving parts to stick together in a problem known as stiction. This is a challenge in the design of micro-electromechanical systems, tiny machines etched onto chips that power sensors, actuators, and advanced electronics. To make these systems function, engineers must learn to account for the invisible push and pull of the vacuum. Researchers are exploring how to turn this challenge into an opportunity. By carefully designing surfaces, materials, and geometries, it is possible to control Casimir forces. Some experiments have shown that under the right conditions, the Casimir effect can even become repulsive rather than attractive. This discovery opens the possibility of creating nanoscale bearings or levitating components that glide without friction. While such devices are still in early stages of research, they demonstrate that the vacuum can be engineered, not as a source of power, but as a field of forces to be harnessed. Beyond nanotechnology, scientists have also speculated about how vacuum fluctuations might influence propulsion. The idea of propelling spacecraft by manipulating the vacuum has often appeared in science fiction, but serious researchers have also explored related concepts. One area of interest is the interaction between quantum fields and strong electromagnetic environments, where unusual effects might be used to create thrust. While no evidence suggests that the vacuum can provide reactionless propulsion, the study of quantum fields in extreme conditions continues to be an active area of inquiry. It reflects the same impulse that drives humanity to dream of harnessing the void, the hope that the unseen might open new frontiers. In the laboratory, experiments continue to reveal subtle ways the vacuum interacts with matter. Cold atom systems, where gases are cooled to near absolute zero, provide platforms to study vacuum fluctuations in controlled settings. In these experiments, atoms suspended in traps or optical lattices feel the influence of zero-point motion and electromagnetic fluctuations. These setups not only confirm the predictions of quantum theory, but also offer insights into how the vacuum shapes the behavior of matter at its most delicate scales. Another frontier is quantum optics. The ability to manipulate light at the level of single photons allows scientists to probe the vacuum directly. Squeeze states of light, created by manipulating vacuum fluctuations, have already been used to improve the sensitivity of gravitational wave detectors. By reducing noise in one property of light, these techniques reveal signals that would otherwise be hidden. The detection of gravitational waves from colliding black holes and neutron stars was made possible in part by shaping the restless background of the vacuum. The emptiness of space thus plays a role in one of the greatest discoveries of modern astronomy. There is also growing interest in the role of the vacuum in materials science. In exotic materials such as metamaterials and topological insulators, the interaction with vacuum fluctuations may create new physical effects. These materials can bend, guide, and shape electromagnetic fields in ways that mimic properties of space-time itself. Studying how the vacuum responds to these artificial structures may reveal new ways to control radiation and information. Again, this is not the extraction of energy, but the shaping of the field, turning emptiness into a participant in technology. Even the idea of propulsion, though still speculative, highlights how seriously scientists take the vacuum. While wild claims of reactionless drives often fail, the continued exploration of quantum field interactions shows that the vacuum is not a passive nothing, but an active medium. By studying how particles emerge in extreme conditions, such as near black holes or in high-energy collisions, physicists hope to learn more about the restless sea of fluctuations. Some even speculate that understanding the vacuum fully may one day allow new kinds of engines, not by breaking the laws of physics, but by applying them in ways not yet imagined. The line between science and fiction is often thin when it comes to the vacuum. On one side are experiments, precise and testable, showing that the vacuum exerts forces, shifts energy levels, and shapes light. On the other side are dreams of infinite power and interstellar drives. The danger is in confusing the two, but the opportunity is in letting the dreams inspire the science, pushing experiments to test what is real and discard what is fantasy. The vacuum may never be a fuel, but it is already a laboratory for some of the most advanced technologies in existence. The pursuit of harnessing the vacuum reflects the human instinct to reach beyond limits Even when the laws of physics deny us free energy, we continue to probe, test, and imagine. And in doing so, we discover that the vacuum is not just a void, but a partner in creation. It cannot be drained, but it can be shaped. It cannot be plundered, but it can be understood. And that understanding carries us farther than fantasy ever could, guiding us toward technologies that turn the invisible into the useful. The dream of free energy has always been part of human imagination. From the earliest attempts at perpetual motion machines to modern claims of zero-point energy devices, people have long hoped for a source of power that requires no fuel, no cost, and no limit. The discovery that the vacuum is filled with restless energy seemed to promise that the dream could at last become real. Here, finally, was an infinite reservoir, present everywhere, impossible to exhaust. But as science probed deeper, the reality became clear. The vacuum is full, but its fullness cannot be harvested. It resists our desires, obeying laws that cannot be broken. This realization can feel disappointing at first. The vision of cities powered forever by the hum of nothingness, or spacecraft propelled by the void, remains in the realm of science fiction. Yet, what physics denies in one sense, it grants in another. The vacuum may not yield unlimited power, but it reveals truths that are no less astonishing. It shows us that emptiness itself is alive, that nothingness has structure, and that the stage on which the universe plays is itself part of the play. The vacuum cannot be our engine, but it is the hidden foundation of every engine, every star, every galaxy. By studying the vacuum, humanity has discovered that nothing is never truly nothing. The Casimir effect, the Lamb shift, and the persistence of zero-point energy in atoms and molecules all prove that empty space has power. This power cannot be drained like oil or coal, but it shapes the way matter behaves and the way technology functions. The vacuum is not a mine to be dug, but a field to be understood. The better we understand it, the more we can design systems that work with its forces, from nanoscale machines to gravitational wave detectors. The pursuit of free energy has also taught us humility. Every claim of a device that defies the laws of physics has eventually failed. Each failure reaffirms the truth that the universe has rules, and those rules cannot be bent by wishful thinking. Yet in those very rules lies beauty. The refusal of the vacuum to give us unlimited power is not a limitation, but a lesson. It tells us that power comes not from fantasy, but from understanding, not from breaking laws, but from working within them. And in working within them, humanity has achieved wonders. By respecting the restless nature of the vacuum, scientists have built technologies that would once have been unimaginable. Quantum computers that manipulate the smallest qubits, sensors that measure gravitational waves across billions of light years, and nanomachines that operate at the scale of atoms. All of these exist because we have learned to shape the vacuum rather than exploit it. The dream of free energy may be unreachable, but the reality is just as extraordinary. On a deeper level, the impossibility of extracting energy from the vacuum highlights a profound truth about our place in the cosmos. We are not masters of the universe, bending it to our will without limit. We are participants, bound by the same rules that govern stars and galaxies. The vacuum is not ours to exploit, but ours to learn from. In this sense, it is less a fuel than a teacher, showing us that the path to progress lies in discovery, not in defiance. At the same time, the vacuum reminds us that we are part of something vast. The same zero-point energy that trembles in atoms also drives the expansion of the universe. The same fluctuations that shift energy levels in hydrogen may also shape the fate of time itself. To imagine drawing power from the vacuum is to imagine harnessing the very breath of the cosmos. We cannot do it. But by studying it, we glimpse the unity of scales, from the tiniest particles to the farthest galaxies. So the dream of harnessing the vacuum ends not with disappointment, but with wonder. We cannot power our cities from nothing, but we can learn that nothing is never empty. We cannot ride the void to the stars, but we can see that the void shapes the stars themselves. The vacuum will not be our engine, but it will be our guide. It points us toward technologies, philosophies, and cosmologies that expand our view of reality. As this chapter closes, the lesson is clear. The vacuum is alive, powerful, and universal, but it is not a source of free energy. Instead, it is a mirror in which we see the limits of our imagination and the depth of nature's laws. It teaches us that to dream is human, but to understand is divine. The journey now turns from human hopes of exploiting the vacuum to the cosmic role it plays in destiny. If the vacuum cannot be our fuel, perhaps it is the very force that decides the future of the universe. The discovery that the vacuum is alive with energy was not only a revolution in physics, but a revelation about the destiny of the cosmos. For most of human history, people assumed the universe was eternal and unchanging, a vast stage upon which stars and galaxies shone forever. Then, in the 20th century, we learned that the universe had a beginning in the Big Bang and has been expanding ever since. In the late 1990s, astronomers discovered that this expansion is not slowing down, but accelerating, driven by the hidden energy of the vacuum. Suddenly, the question of the fate of everything became inseparable from the mystery of nothing. If the vacuum energy remains constant, as the simplest version of Einstein's cosmological constant suggests, the universe will expand forever. The repulsive pressure of the vacuum will continue to stretch space at an accelerating pace. Over billions of years, galaxies not bound to us by gravity will recede beyond the horizon of visibility. Their light will be stretched into wavelengths too long to detect, and they will vanish from sight. The universe will grow emptier and lonelier with each passing era as cosmic neighbors slip beyond reach. In trillions of years, only the galaxies of our local group, the Milky Way, Andromeda, and a few smaller companions, will remain bound together by gravity. These galaxies will eventually merge into a single massive structure, while all others disappear into the darkness. The stars within this merged galaxy will continue to shine for a time, but gradually they will burn out one by one. Red dwarfs will exhaust their fuel, white dwarfs will cool into black dwarfs, and neutron stars will fade into obscurity. The night sky, once filled with countless points of light, will dim until it is nearly black. This vision is called the heat death of the universe. It is not a sudden event, but a slow, inexorable fading. As expansion accelerates, matter thins, energy dissipates, and temperature approaches a uniform minimum. Black holes will remain as the last luminous objects, but even they will eventually evaporate through Hawking radiation, vanishing into faint wisps of energy. What remains is a cosmos dominated entirely by the vacuum, vast, dark, and silent. In this scenario, the vacuum defines the end state of time. It becomes the final ruler of the cosmos, erasing the structures built by matter and energy. Galaxies, stars, planets, and life itself are temporary flickers, while the vacuum endures. If vacuum energy is truly constant, then the universe will expand eternally. But expansion will also mean emptiness. The story ends not with a cataclysm, but with an infinite stillness, a horizon that recedes forever, and a silence that no star can break. Yet even in this bleak vision, there is wonder. The same vacuum energy that accelerates galaxies apart also ensures that the universe does not collapse in a fiery end. It guarantees infinite time and infinite space, even if most of it is empty. the vacuum preserves existence itself, even as it dissolves structure. This duality, creator of eternity, destroyer of form, makes vacuum energy one of the most profound features of reality. The possibility of eternal expansion raises deep philosophical questions. What does it mean for the universe to have no end, but only endless fading? Is eternity meaningful if nothing remains to witness it? The vacuum here becomes not only a physical presence, but a philosophical horizon, forcing us to confront the limits of existence. The fate of galaxies and stars is written in the equations of quantum fields, and the silence of the future is dictated by the hum of empty space. But constant vacuum energy is only one possibility. The universe may not follow such a quiet path. If the vacuum energy changes with time, the future could be far more dramatic. The next possibilities reveal fates that are not gentle fading, but violent transformation, where the vacuum itself reshapes everything. The picture of eternal expansion assumes that vacuum energy is constant, the same today as it was billions of years ago, and the same as it will be trillions of years from now. But what if the vacuum is not fixed? What if the energy of empty space changes over time? This possibility opens doors to futures far more violent and unpredictable than slow fading. If the vacuum evolves, the universe could face fates both catastrophic and reborn. One scenario is called the Big Rip. In this vision of the future, the vacuum energy does not remain constant, but grows stronger with time. Instead of merely accelerating the expansion, it accelerates it faster and faster until every structure in the universe is torn apart. First, distant galaxies recede so quickly that their light can no longer reach us. Then, clusters of galaxies are pulled apart. Later, individual galaxies themselves are shredded, their stars flung into the darkness. As the vacuum energy continues to rise, even solar systems become unstable. Planets are pulled from their stars, moons from their planets. Eventually, stars themselves are ripped apart. And finally, atoms are torn asunder, their protons and neutrons separated by the relentless expansion. In the Big Rip scenario, the universe ends not with quiet darkness, but with catastrophic disintegration. Every bond, from cosmic to atomic, is undone. The entire fabric of reality unravels under the pressure of a vacuum that refuses to rest. The timeline depends on how quickly the vacuum energy grows, but in extreme versions of the scenario, the end could come in tens of billions of years. Though distant compared to human lifetimes, it is not infinitely far away. If the vacuum evolves in this way, the universe's story is one of acceleration without end, culminating in destruction. Another possibility is the reverse, that vacuum energy weakens with time. If the repulsive effect diminishes, gravity could eventually regain dominance. The expansion might slow, halt, and then reverse into contraction. In this case, the universe would collapse in a catastrophic big crunch. Galaxies would rush together, stars would collide, and temperatures would soar. Space and time would fold back into the dense state from which they began. Some cosmologists suggest that such a collapse could even trigger a new Big Bang, starting the cycle anew. In this view, the universe might not have one birth and one death, but an infinite series of cycles, driven by the ebb and flow of vacuum energy. These scenarios are speculative, but not impossible. The key lies in whether dark energy, the modern name for the vacuum's repulsive influence, is truly constant, or whether it evolves. Observations so far suggest that it is constant, but the measurements are not yet precise enough to rule out slow changes. This is why astronomers continue to measure the expansion of the universe with increasing accuracy. If dark energy evolves, it will reveal itself over cosmic time, and the fate of everything will change. Even more exotic is the possibility of vacuum decay. quantum field theory allows that the vacuum we inhabit may not be the absolute lowest energy state of reality. Instead, it could be a false vacuum, a local minimum in the energy landscape. If a lower true vacuum exists, the universe could someday transition to it in a catastrophic event. A bubble of true vacuum could form and expand at nearly the speed of light, rewriting the laws of physics inside it. In this scenario, no warning would come, and the entire universe would be transformed instantly. The vacuum itself would decide the future, not by evolving slowly, but by collapsing suddenly into a new state. These possibilities show that the fate of the cosmos is written in the properties of the vacuum. If it is constant, the future is an eternal fade into darkness. If it grows, the Big Rip tears everything apart. If it weakens, the Big Crunch ends the story in fire. If it decays, a sudden phase transition resets reality itself. Each outcome depends not on the stars or galaxies, but on the hum of empty space, the same vacuum that trembles in atoms and fuels cosmic acceleration. The uncertainty is profound. Humanity cannot yet know which future awaits. What we do know is that the vacuum, once dismissed as nothing, is the deciding force in the ultimate destiny of the universe. The emptiness between galaxies will write the final chapter of time. Vacuum energy does more than shape the present universe. It may decide how the story ends. If it is constant, expansion will continue forever until stars die and galaxies vanish beyond view, leaving only darkness. But if it evolves, the future could be far more dramatic. Physicists consider the possibility that our vacuum is not the true lowest state of reality. In quantum field theory, fields can have false vacua, states that look stable but are not absolute. If our universe sits in such a state, it could someday tunnel into a deeper vacuum. A bubble of true vacuum would form and expand at nearly the speed of light. Inside, the laws of physics could change. Particles, forces, even the fabric of chemistry could be rewritten. For anything caught inside, the transformation would be instant and final. No warning would come. Though unsettling, this possibility is not fantasy but mathematics. Vacuum decay is a natural prediction of quantum field theory, though whether it is likely in our universe is unknown. Some calculations suggest that the Higgs field, discovered in 2012, could make our vacuum metastable. If so, the universe might one day collapse into a new state. Yet the timescales for such events are vast, possibly far longer than the lifespan of stars or black holes. What these scenarios reveal is that the vacuum is not passive. It is the foundation upon which reality stands. And if that foundation shifts, everything built upon it changes. The fate of galaxies, stars, and life is bound not to matter, but to the properties of nothing. The vacuum is not only the background of the cosmic play, it is the author of the final act. As this chapter closes, one truth is clear. Whether the universe ends in quiet expansion, violent rip, crushing collapse, or sudden transformation, the deciding force is the vacuum. Emptiness holds the future in its hands. What we once imagined as nothing has become the most important something of all. For most of history, people imagined nothingness as absence. Ancient philosophers argued over whether a void could exist at all. Aristotle denied it, while later thinkers pictured it as a hollow backdrop for matter. Modern science has overturned these views. The vacuum is not absence. It is full, restless, and decisive. Nothing, as it turns out, is the most powerful something in existence. Quantum mechanics revealed this first. Zero-point energy ensures that even in the lowest state, fields vibrate. The Casimir effect proved that empty space exerts measurable force. Cosmology extended the lesson to the largest scales, showing that the vacuum dominates the universe driving its acceleration and shaping its destiny. What once seemed like a silent backdrop is now the stage, the actor, and the author of the cosmic drama. This realization is more than scientific. It carries deep philosophical weight. If nothing has energy, then absence itself is presence. The silence of the vacuum is not emptiness, but a hidden symphony. It erases the boundary between being and non-being, between physics and metaphysics. The ancient question, can nothing exist, now has an answer. Nothing cannot exist because even emptiness is alive with energy. The lesson humbles humanity. We once believed that matter was the foundation of the universe, but we now see that matter is secondary. The true foundation is the vacuum, the invisible field that sustains galaxies, stars, and life. Its energy is small but decisive, its presence subtle but universal. It is the hidden fabric upon which existence itself is embroidered. As we look to the future, the vacuum remains both mystery and guide. We cannot mine it for free energy, but we can learn from its restless hum. It defines the structure of atoms, the expansion of galaxies, and the fate of time. In it, we see the link between the smallest and the largest scales, between the measurable and the philosophical. The story ends with the deepest truth science has yet uncovered. Emptiness is not empty. The vacuum is alive, powerful, and eternal. It is the quiet force that binds the universe together and decides its end. In the silence of empty space lies the loudest truth of all. Nothing is never truly nothing.